Hello there, and welcome. Tonight I want to take you somewhere far beyond the familiar glow of city lights, beyond the gentle pull of Earth's gravity, beyond even the warm embrace of our sun's light. Tonight we're going to drift together into the vast quiet darkness between the stars, where an ancient traveller has been sailing through the cosmic void for perhaps millions of years, carrying secrets we're only beginning to imagine. It's a question that might seem impossibly distant from our everyday concerns, but what if this cosmic wanderer, this mysterious object we call 3i Atlas, was actually rewinding history itself, carrying within its frozen heart the story of how worlds begin, how life might emerge, and how the universe writes its endless narrative across the canvas of space and time? You know, there's something profoundly peaceful about contemplating objects that move through space on timescales that dwarf our human experience. As you settle in tonight, perhaps adjusting your pillow, finding that perfect comfortable position, I invite you to let your mind drift with me into this cosmic mystery. And if you find yourself drawn to these gentle explorations of the universe's secrets, consider subscribing to our channel, where each night we unravel another thread in the vast tapestry of space, always with the same quiet wonder, the same peaceful curiosity that transforms the unknown from something frightening into something beautiful. The subscribe button waits patiently, just as the stars do, whenever you're ready to join us on more of these tranquil journeys through the cosmos. The story of 3i Atlas begins not with a dramatic discovery, not with alarms or urgent announcements, but with a faint smudge of light captured by patient telescopes scanning the darkness. Imagine, if you will, astronomers at their stations, perhaps sipping coffee in the pre-dawn hours, when suddenly their instruments detect something unusual, something that doesn't quite fit the familiar patterns of our solar system's regular inhabitants. This wasn't a comet born from our own Oort cloud, that vast sphere of icy bodies that surrounds our sun like a gossamer shell. No, this was something else entirely, something that had been travelling through the emptiness between stars for longer than human civilization has existed, longer perhaps than complex life has flourished on Earth. The designation 3i Atlas might sound clinical, almost dismissive, but within those characters lies a profound statement about what this object represents. The I stands for interstellar, marking this as only the third confirmed object we've ever detected that originated from beyond our solar system. Think about that for a moment. In all of human history, with all our observations of the night sky, from ancient astronomers charting the movements of planets, to modern scientists wielding telescopes that can peer billions of light years into space, we've only confirmed 3 visitors from the vast ocean of interstellar space. It's as if we've been standing on a cosmic shore for millennia, and only 3 times have we found a message in a bottle washed up from distant seas. When we say interstellar, we're not just talking about something from far away, we're talking about an object that has crossed the almost unimaginable emptiness between star systems. If you compress the entire solar system down to the size of a dinner plate, the nearest star would still be about 4 miles away, and between those dinner plates, nothing but darkness, cold, and silence. Yet somehow, 3i Atlas navigated that void, maintaining its course through regions where the temperature hovers just barely above absolute zero, where a single atom might travel for years without encountering another, where time itself seems to slow to a crawl, in the absence of any markers by which to measure its passage. Consider the journey this object has taken. While we've been building civilizations, discovering fire, inventing the wheel, developing language, creating art, falling in love, raising children, and pondering our place in the universe, 3's Atlas has been sailing through the darkness. It has been a silent witness to the slow dance of distant stars, perhaps passing through regions where new stars are being born in vast stellar nurseries, or drifting past the expanding shells of ancient supernovae. Its surface has been bombarded by cosmic rays for eons, each particle impact leaving its mark like a timestamp on an ancient document. The discovery of 3i Atlas wasn't accompanied by fanfare or breaking news alerts. Instead, It emerged quietly from the data, like a whisper in a library. Astronomers noticed its trajectory first, that telltale sign that it wasn't bound to our sun's gravity, but was instead just passing through, like a traveller who stops briefly at a roadside rest area before continuing on an endless highway. The hyperbolic orbit, as scientists call it, is nature's way of telling us that this object has too much energy to stay, that it's moving too fast to be captured by our sun's gravitational embrace. It will swing past our star, perhaps warming slightly in its glow, and then continue back into the darkness, never to return. But during its brief passage through our neighbourhood, 3i Atlas offers us an extraordinary opportunity. It's as if the universe has sent us a time capsule not from our own past, but from the history of another star system entirely. Every molecule within this cosmic visitor, every grain of dust, every frozen gas, tells a story about conditions in a place we may never be able to visit directly. It carries within it the chemical fingerprints of its birthplace, the isotopic ratios that reveal the nature of the star around which it once orbited, perhaps billions of years ago. The name Atlas itself comes from the telescope system that helped identify this visitor, but there's a poetic appropriateness to it as well. In Greek mythology, Atlas was the titan who held up the heavens, bearing the weight of the celestial sphere on his shoulders. Our 3i Atlas, in its own way, carries the weight of cosmic history, holding within its structure information about how planetary systems form and evolve in distant corners of our galaxy. It's a burden it has carried silently through the darkness, waiting for someone somewhere to notice its passage and decode its secrets. As we observe this object, we're not just looking at a chunk of rock and ice. We're looking at a piece of another world story, frozen in time and delivered to our doorstep by the patient mechanics of orbital dynamics and chance encounters. The odds of such an object passing close enough for us to detect it are astronomically small. Space is so vast, so empty, that most interstellar objects pass through our solar system completely unnoticed. Too far from Earth for our instruments to detect, too faint for our telescopes to see. The fact that we've spotted 3i Atlas at all is a reminder of how much might be passing by unseen, how many cosmic messages might be drifting through the darkness, just beyond our ability to perceive them. What makes 3i Atlas particularly intriguing is not just that it comes from another star system, but what it might tell us about the concept of history itself on a cosmic scale. When we look at objects in our own solar system, we're looking at materials that have been processed and reprocessed through billions of years of planetary evolution. Comets from our Oort cloud preserve some primordial materials, but even they have been influenced by our sun's radiation, by gravitational perturbations from our planets, by the particular conditions of our solar system's formation. But 3i Atlas offers us something different. A sample of materials that evolved under completely different conditions, around a different star, in a different epoch of galactic history. Perhaps this object formed when its parent star was young and vigorous, surrounded by a protoplanetary disk rich in heavy elements, forged in previous generations of stars. Or perhaps it comes from an older, more metal-poor system, where the building blocks of planets were scarcer, where worlds formed differently than they did here. Each possibility tells us something about the diversity of planetary systems in our galaxy, about the many ways that matter can organize itself around stars, about the countless variations on the theme of cosmic evolution playing out across the Milky Way. The surface of 3i Atlas has been exposed to interstellar space for so long that it has likely been fundamentally altered by its journey. Cosmic rays, those high-energy particles that zip through space at nearly the speed of light, have been striking its surface for millions of years, creating a processed outer layer that scientists call a radiation mantle. This crust of altered material is itself a record of the object's journey, a kind of travel diary written in damaged molecular bonds and exotic isotopes. Beneath this weathered exterior, however, might lie pristine materials that have been preserved since the object's formation, protected from the harsh environment of interstellar space by the sacrificial outer layers. Think about what that means. Inside 3i Atlas could be materials that have been essentially frozen in time since before our solar system existed. These could be the original building blocks from which planets formed around another star, preserved like insects in amber, waiting billions of years for someone to discover them and read the story they tell. It's as if we've been given a core sample not from Earth's geological history, but from the geological history of an entirely different world, or perhaps from the time before worlds, when everything was still dust and gas swirling in the darkness. The trajectory of 3i Atlas tells its own story. By carefully measuring its path through our solar system, astronomers can work backwards, tracing its route through interstellar space like detectives following a trail of cosmic breadcrumbs. This orbital archaeology suggests that the object has been travelling for an enormously long time, perhaps millions of years since it left its home system. During that time, it has been subject to the gentle gravitational tugs of distant stars, each encounter slightly altering its path like a pinball bouncing through a cosmic arcade in extreme slow motion. But here's where things get really interesting. The concept of rewinding history takes on a special meaning when we consider what 3i Atlas might be carrying. If this object contains organic molecules, the complex carbon-based compounds that are the precursors to life, then it might be carrying the seeds of biology from another star system. Not life itself necessarily, but the chemical ingredients from which life could potentially arise. These molecules, if they exist within 3i Atlas, would have formed under different conditions than similar molecules in our solar system, perhaps following different chemical pathways, exploring different molecular possibilities. Imagine if 3i Atlas contains water ice, as many comets do, but this wouldn't be water that condensed from the solar nebula that gave birth to our sun and planets. This would be water from another stellar nursery entirely, water molecules that might have formed billions of years ago around a different star, under different temperatures and pressures, in the presence of different chemical catalysts. The hydrogen and oxygen atoms in that water would be identical to those in Earth's oceans, of course, because the laws of physics are universal. But the story of how those atoms came together, the cosmic history encoded in their arrangement, would be entirely different. Scientists have speculated that objects like 3i Atlas might play a role in spreading organic chemistry throughout the galaxy. This idea, sometimes called panspermia or pseudo-panspermia, suggests that the building blocks of life might be distributed between star systems by wandering comets and asteroids. It's not about spreading life itself, but about spreading the complex molecules from which life might eventually arise. If this is true, then 3i Atlas isn't just rewinding history. It's potentially carrying history forward, delivering ancient chemical messages to new star systems, including our own. The faintness of 3i Atlas speaks to both its size and its surface properties. This is not a giant object. It's probably no more than a few kilometers across, a tiny speck in the vastness of space. Yet within that small volume could be compressed billions of years of cosmic history. Every dust grain, every molecule, every atom has a story to tell about where it came from and how it got here. The darkness of its surface suggests it might be covered in organic compounds, complex carbon molecules that absorb light rather than reflecting it. These dark materials are common in our outer solar system, but the ones on 3i Atlas would have formed under alien suns in alien conditions. As our telescopes track this visitor, we're reminded of how much we still don't know about our cosmic neighborhood. For every object like 3i Atlas that we detect, there might be thousands or millions that pass by unnoticed. The interstellar medium, that vast space between the stars, might be populated with countless such wanderers, each carrying its own cargo of cosmic history, each telling its own story about the formation and evolution of planetary systems throughout the galaxy. We're only just beginning to develop the technology to detect these objects, to read the messages they carry. The study of 3i Atlas represents a new kind of astronomy, one that doesn't just observe distant objects but actually examines physical samples from other star systems. It's as if we've been reading about foreign countries in books and suddenly a visitor arrives at our door carrying artifacts from those distant lands. We can't travel to other star systems, not with our current technology, not within human lifetimes. But in a sense, those star systems are coming to us, sending their emissaries through the darkness, allowing us to touch, however briefly, materials that formed under alien suns. Consider the profound shift in perspective this represents. For all of human history, we've been confined to one star system, able to study only the materials that formed around our own sun. Every rock we've examined, every sample we've analysed, every meteorite that has fallen to Earth, all came from the same stellar neighbourhood. But with objects like 3i Atlas, we're breaking free of that limitation. We're beginning to sample the true diversity of the galaxy, to understand how our solar system fits into the broader context of planetary formation throughout the cosmos. The questions raised by 3 Atlas go beyond simple scientific curiosity. They touch on fundamental issues about our place in the universe, about the uniqueness or commonality of our cosmic situation. If the materials in this interstellar visitor are radically different from what we find in our own solar system, it might suggest that planetary formation is highly variable, that each star system is unique in its own way. But if we find familiar chemicals, similar compositions, comparable structures, it might indicate that the processes that built our solar system are universal, that worlds throughout the galaxy might be more similar than different. There's something deeply humbling about detecting an object like 3i Atlas. It reminds us that our solar system is not a closed system, not an island isolated in space, but part of a vast, interconnected galaxy where materials and perhaps even information flow between the stars over cosmic timescales. We tend to think of interstellar space as empty, as a barrier between star systems, but objects like 3i Atlas show us that it's actually a highway, albeit one where the traffic moves very, very slowly. The detection of this object also raises intriguing questions about the early solar system. If interstellar objects pass through our neighbourhood regularly, even if most go undetected, then some must have passed through billions of years ago when our planets were still forming. Could some of the materials that make up Earth, Mars, or the other planets have originally come from other star systems? Could there be interstellar immigrants buried in our planet's core, or orbiting in our asteroid belt, indistinguishable now from native materials but carrying within them the legacy of distant stars? This possibility transforms our understanding of planetary formation from a local process to a galactic one. Each star system might not be forming in isolation, but might be sampling materials from across the galaxy, incorporating interstellar wanderers into growing planets, mixing and matching chemical ingredients from multiple stellar sources. If this is true, then every planet, including Earth, is partly made from cosmic immigrants, from materials that began their journey around other stars and travelled through interstellar space before finding a new home. The story of 3i Atlas also connects to broader questions about time and cosmic evolution. This object has existed for so long that it predates many of the stars we see in our night sky. While it was drifting through space, stellar nurseries were giving birth to new suns, some of which have already lived out their lives and died. Civilizations might have risen and fallen on planets orbiting stars that didn't even exist when 3 Atlas began its journey. It's a reminder that the universe operates on timescales that dwarf human experience, that cosmic processes unfold with a patience we can barely comprehend. Yet despite these vast timescales, there's an immediacy to observing through Atlas. Right now, as you listen to these words, this ancient object is moving through our solar system at tremendous speed. Every second, it travels dozens of kilometers, eating up the distance between planets in a matter of weeks or months. Its visit is brief on cosmic scales, a fleeting encounter that will be over in just a few years. Then it will return to the darkness, continuing its eternal journey through interstellar space, perhaps not to encounter another star system for millions of years. This transient nature of the encounter adds poignancy to our observations. We have only a short window to study this visitor, to extract whatever secrets it might hold. Every observation is precious, every data point valuable, because once 3i Atlas leaves our solar system, it's gone forever. We'll never see this particular object again, never have another chance to study these specific materials from this specific star system. It's a reminder of how many opportunities might pass us by, how many cosmic messages might drift through our neighborhood unread, simply because we weren't looking in the right direction at the right time. The idea that 3i Atlas might be rewinding history becomes even more compelling when we consider what it might tell us about the chemical evolution of the galaxy. The elements that make up this object, the ratios of different isotopes, the molecular compositions, all of these factors can tell us about the conditions in the galaxy when and where it formed. If 3i Atlas is very old, it might preserve information about the galaxy's chemical composition billions of years ago, before many cycles of stellar birth and death had enriched the interstellar medium with heavy elements. Think of it as a core sample, not from Earth's ice sheets or ocean floors, but from the galaxy itself. Each layer of material in 3i Atlas might record different epochs in its history, different environments it has passed through, different processes it has undergone. By studying these layers, if we could access them, we might be able to reconstruct not just the history of this one object, but broader patterns of galactic evolution, the slow enrichment of the cosmos with the elements necessary for planets and life. The surface chemistry of 3i Atlas is particularly intriguing. After millions of years in interstellar space, exposed to cosmic rays and the extreme cold of the void, what kinds of chemical reactions might have taken place? Some scientists speculate that the surfaces of interstellar objects might be laboratories for exotic chemistry, places where reactions that would never occur under normal conditions can proceed, albeit very slowly. The products of these reactions, these chemicals forged in the darkness between stars, might be unlike anything we can create in Earth laboratories. Perhaps there are complex organic molecules on 3i Atlas that form through processes we don't yet understand, catalyzed by cosmic rays over millions of years. Perhaps there are crystalline structures that could only form under the precise conditions of interstellar space, where temperatures hover just above absolute zero, and pressures are essentially non-existent. These materials, if they exist, would be treasures for science, examples of what the universe can create when given enough time and the right conditions. The gravitational archaeology that allows us to trace 3i Atlas's path also tells us something about the dynamics of our galaxy. This object has been influenced by the gravity of many stars during its journey, each encounter slightly altering its trajectory. By working backwards from its current path, astronomers can estimate not just where it came from, but what route it took to get here. This is like reading a travel diary written in orbital mechanics, each gravitational encounter a stamp in a cosmic passport. But the path of 3i Atlas also reminds us of the role of chance in cosmic encounters. If this object had passed through our solar system just a few decades earlier, before we had the telescopes capable of detecting it, we would have missed it entirely. If it had taken a slightly different path through interstellar space, it might have passed too far from Earth for us to see. The fact that we detected it at all is a fortunate accident, a cosmic coincidence that allows us this brief glimpse into the broader galaxy. As we contemplate 3i Atlas, we're also contemplating our own future. Just as this object is a visitor to our solar system, our sun and planets are themselves moving through the galaxy, orbiting the galactic center once every 250 million years or so. During these galactic orbits, we pass through different regions of space, encountering different stellar neighborhoods, different densities of interstellar material. In a sense, our entire solar system is on its own journey through the cosmos, and objects like 3i Atlas remind us that we're not traveling alone. The study of interstellar objects like 3i Atlas is also pushing the boundaries of our technology and observation techniques. Detecting such faint, fast-moving objects requires sophisticated telescopes and data processing systems. It requires international cooperation, with observatories around the world working together to track these cosmic visitors. It requires new theoretical frameworks to understand what we're seeing, new models to interpret the data. In pushing us to observe and understand these objects, 3i Atlas is also pushing us to advance as a scientific civilization. There's a beautiful symmetry in the idea that as we study 3i Atlas, we're also preparing for future interstellar visitors. Each object we detect teaches us something new, helps us refine our techniques, improves our ability to spot and study the next one. We're building a catalogue of interstellar objects, each one a data point in our understanding of the galaxy's diversity. Over time, as we detect more such visitors, patterns might emerge, revealing deeper truths about how star systems exchange materials, how the galaxy mixes and redistributes its chemical ingredients. The possibility that 3i Atlas might contain water ice or organic molecules also connects to questions about the origin of life on Earth. We know that the early Earth was bombarded by comets and asteroids, which might have delivered water and organic compounds that contributed to the emergence of life. But what if some of those impactors were themselves interstellar visitors? What if Earth's oceans contain a small fraction of water from other star systems? What if some of the organic molecules that gave rise to life on our planet originally formed around alien suns? These questions might seem speculative, but they're grounded in real possibilities. If objects like 3i Atlas have been passing through our solar system throughout its history, and if even a small fraction of them collided with the forming Earth, they could have contributed materials to our planet's inventory. This would mean that Earth, and by extension all life on Earth, is partly made from interstellar materials, that we are, in a very real sense, children not just of our own star, but of the galaxy as a whole. As 3i Atlas continues its passage through our solar system, it's also continuing its own evolution. The warmth of our sun, faint as it might be at the object's distance, could be causing subtle changes to its surface. Volatile compounds that have been frozen for millions of years might be sublimating, turning directly from solid to gas and escaping into space. This process, if it's happening, would be revealing deeper layers of the object, layers that have been protected from interstellar radiation, layers that might preserve even more ancient materials. Imagine if we could somehow sample those escaping gases, capture some of the molecules that 3i Atlas is shedding as it passes through our solar system. Each molecule would be a messenger from another star system, a physical piece of another world story. The technology to do this doesn't quite exist yet, but future missions might be able to intercept and study interstellar objects to actually touch materials from other star systems. 3i Atlas is showing us what's possible, what kinds of science we might be able to do if we're prepared for the next interstellar visitor. The name Rewinding History in our title tonight takes on multiple meanings as we consider 3i Atlas. On one level, we're literally looking back in time, studying an object that might have formed billions of years ago. On another level, we're rewinding the object's journey, tracing its path back through interstellar space to understand where it came from. And on yet another level, we're using this object to rewind our understanding of cosmic history, to glimpse conditions in the galaxy long before our solar system existed. But perhaps the most profound aspect of rewinding history is the way 3i Atlas challenges us to think about time itself on cosmic scales. This object has existed in a kind of suspended animation for millions of years, its materials largely unchanged as it drifted through the darkness. It's as if time has moved more slowly for 3i Atlas than for the bustling star systems it has passed. Now, as it encounters our sun, it's briefly rejoining the flow of cosmic time, warming, changing, evolving, before returning to its long, cold sleep in interstellar space. The patience required for interstellar travel, even for an inanimate object like 3i Atlas, is almost incomprehensible. While this object has been travelling, entire species have evolved and gone extinct on Earth. Mountain ranges have risen and been worn away. Continents have drifted across our planet's surface. The constellations visible from Earth have shifted as our Sun and the other stars have moved through space. Yet through all of this change, 3E Atlas has simply continued on its path, a constant in a universe of variables. This cosmic patience offers a different perspective on our own existence. Our lives, our civilizations, even our species are brief flickers in cosmic time. Yet we're here at just the right moment to observe 3I Atlas, to wonder about its origins, to speculate about its composition. In the vast lottery of cosmic timing, we've won a small prize, the chance to witness this ancient traveller's passage through our neighbourhood. It's a reminder that while our individual lives are brief, we're part of something much larger and longer lasting, a cosmic story that has been unfolding for billions of years and will continue long after we're gone. Now we trace the path of our silent visitor, and in doing so, we begin to comprehend the almost impossible scale of its journey. When we speak of 3 Atlas as an interstellar object, we're not simply describing something from far away, we're describing something that has crossed the cosmic desert. The vast emptiness between stars where matter is so sparse that a single atom might travel for years without encountering another. This is a realm so different from our everyday experience that we need new ways of thinking, new metaphors and comparisons to even begin to grasp what such a journey entails. Let me paint you a picture of scale that might help your mind wrap around these distances. If we shrunk our entire solar system down so that Earth's orbit around the Sun was just 1 inch across, Neptune's orbit would be about a foot in diameter. At this scale, you could hold our entire solar system in your hands like a dinner plate. But to reach the nearest star, Proxima Centauri, you would need to walk about 4 miles. 4 miles of emptiness, with nothing but the occasional hydrogen atom, the rare dust grain, the whisper of magnetic fields and radiation that permeate the cosmic void. And 3I Atlas has crossed distances like this, perhaps many times over, in its journey to reach us. The path of an interstellar object is not a straight line, but a complex curve through space and time, influenced by the gravity of every star it passes, however distantly. Imagine a marble rolling across an infinite rubber sheet that has been deformed by the weight of billions of bowling balls, each one representing a star. The marble doesn't move in a straight line but follows the curves and dips in the sheet, its path constantly but subtly altered by the gravitational landscape it traverses. This is how 3I Atlas has moved through the galaxy, its trajectory a record of every gravitational encounter, every stellar system it has passed, even if only at enormous distances. When astronomers first detected 3I Atlas and calculated its orbit, they discovered something remarkable. This object is moving through our solar system at a speed that tells us it cannot possibly be from here. It's travelling too fast to be gravitationally bound to our Sun, moving with what scientists call excess velocity. This excess speed is like a passport stamp from interstellar space, proof that this object has been falling through the galaxy's gravitational field for an enormously long time, accumulating speed from countless gentle tugs of distant stars. The velocity of 3I Atlas relative to our Sun is measured in tens of kilometers per second, speeds that are difficult for our earthbound minds to comprehend. At these speeds, you could travel from New York to Los Angeles in about 2 minutes. You could circumnavigate the Earth in about 20 minutes. You could reach the Moon in just a few hours. Yet even at these tremendous velocities, the journey between stars takes millions of years. This is the paradox of interstellar space. Everything moves incredibly fast, yet everything takes an incredibly long time. To understand the path that brought 3 Atlas to us, astronomers work like forensic investigators at a cosmic crime scene. They measure the object's current position and velocity with extreme precision, then run the cosmic clock backwards, accounting for the gravitational influence of our Sun, our planets, and even the general gravitational field of our galaxy. This process, called orbital backtracking or trajectory reconstruction, allows them to trace where 3I Atlas has been, like following breadcrumbs through a dark forest, except the forest is light years wide, and the breadcrumbs are mathematical calculations. The results of these calculations are both precise and uncertain, a paradox that captures the nature of studying interstellar objects. We can say with high confidence what general direction 3I Atlas came from, which section of sky it emerged from before entering our solar system, but the farther back we trace its path, the more uncertain it becomes. Small uncertainties in our current measurements compound over time, and the gravitational influences of stars we don't even know about could have altered its trajectory in ways we can't calculate. It's like trying to determine where a message in a bottle was thrown into the ocean by studying the currents, except the ocean is three-dimensional. The currents are invisible, and the bottle has been drifting for millions of years. What we can say is that 3I Atlas appears to have come from the general direction of the constellation Lyra, though this doesn't mean it originated from any of the stars we see in that constellation. Those stars are at vastly different distances from us, and millions of years ago, when 3I Atlas might have begun its journey, they were in completely different positions. The constellation Lyra as we see it is a two-dimensional projection of three-dimensional space, like looking at a forest from one angle and trying to determine which tree a bird flew from. The bird might have come from a tree you can't even see from your vantage point, hidden behind others or too far away to distinguish. The journey of 3I Atlas through interstellar space would have been lonely beyond imagination. For millions of years, this object has been falling through darkness, with no star close enough to provide warmth or light. The temperature of interstellar space is about 2.7 degrees above absolute zero, the background temperature of the universe itself, a cold so profound that most molecular motion essentially stops. In this environment, 3I Atlas would have been in a kind of cosmic hibernation, its materials locked in place, its chemistry frozen, waiting for the warmth of a star to awaken it. During its interstellar journey, 3I Atlas would have been bombarded by cosmic rays, those high-energy particles that zip through space at nearly the speed of light. These particles, mostly protons but also including heavier atomic nuclei, would have struck its surface with enormous energy, capable of breaking molecular bonds, creating new isotopes, and gradually transforming the outer layers of the object. This cosmic ray processing is like a very slow form of erosion, not wearing away the surface mechanically but altering it at the atomic level, creating a rind of radiation-damaged material that scientists call a radiation mantle. The interstellar medium through which 3I Atlas travelled is not completely empty, though it comes close. On average, there's about 1 hydrogen atom per cubic centimetre in interstellar space, though this density varies considerably. In some regions, called molecular clouds, the density can be thousands of times higher, while in the vast bubbles blown by supernova explosions, it can be even lower. As 3I Atlas moved through these different environments, it would have encountered different conditions, different levels of radiation, different magnetic fields, each leaving subtle marks on its surface and structure. Think about the sheer duration of this journey. When 3I Atlas left its parent star system, whenever that was, Earth might have been a very different place. If it has been travelling for 10 million years, it began its journey when our ancestors were early apes, when the Sahara was a lush forest, when the Mediterranean Sea had dried up into a vast salt desert. If it has been travelling for 100 million years, it left home when dinosaurs ruled the Earth, when flowering plants were just beginning to evolve, when the Atlantic Ocean was much narrower than it is today. And if it has been travelling for 1 billion years, it began its journey when complex life on Earth consisted of nothing more than single-celled organisms, when our planet's atmosphere contained almost no oxygen, when the day was only about 18 hours long because Earth was spinning faster. The path of 3I Atlas is also influenced by the overall rotation of our galaxy. The Milky Way is not a static structure but a dynamic rotating system, with stars orbiting the galactic centre at different speeds depending on their distance from it. Our Sun takes about 250 million years to complete one orbit around the galaxy, a period sometimes called a cosmic year or galactic year. During the journey of 3i Atlas, depending on how long it has been travelling, our entire galaxy might have rotated significantly, with stars changing their relative positions, spiral arms winding and unwinding, stellar nurseries forming and dispersing. This galactic rotation adds another layer of complexity to understanding the origin of 3i Atlas. Even if we could trace its path perfectly, the star it came from might now be in a completely different part of the galaxy. It's like trying to find someone's childhood home in a city where all the buildings have been moved around multiple times. The stellar neighborhood that gave birth to 3i Atlas might no longer exist in any recognizable form, its stars having dispersed across thousands of light years, its gas and dust incorporated into new generations of stars and planets. The hyperbolic trajectory of 3 Atlas through our solar system is a beautiful example of celestial mechanics in action. As it approached our sun, it began to accelerate, pulled by our star's gravity. This acceleration caused it to curve toward the sun, but its initial speed was so great that gravity couldn't capture it. Instead, it's following a hyperbolic path, swinging past our sun like a cosmic slingshot, using our star's gravity to change direction but not to slow down enough to stay. This type of orbit is fundamentally different from the closed elliptical orbits of our planets and comets, which are gravitationally bound to the sun and will return again and again. The shape of this hyperbolic path tells us something profound about the nature of 3i Atlas. It confirms beyond doubt that this object is not from here, that it's a true visitor from interstellar space. No amount of gravitational perturbation from our planets could give a native solar system object enough energy to achieve such a trajectory. It would be like finding a baseball in your backyard moving so fast that you know it couldn't have been hit by anyone in your neighborhood, or even your city. It must have come from much farther away, carrying energy from a very distant source. As 3i Atlas moves through our solar system, it's experiencing something it might not have encountered for millions of years: the warmth of a star. Even at its considerable distance from our sun, it's receiving more heat and light than it has in eons. This warming might be causing subtle changes to its surface, perhaps releasing gases that have been frozen since before our solar system existed. These releases, if they're happening, would create a thin atmosphere around the object, a temporary envelope of gas that will dissipate as it returns to interstellar space. The gravitational influence of our planets on 3i Atlas is minimal but measurable. Jupiter, the giant of our solar system, might deflect its path by a tiny amount. Saturn, Uranus, and Neptune might add their own minute contributions. These deflections are so small that they're difficult to measure, but they're part of the object's story, new chapters being written in its long journey. When 3i Atlas leaves our solar system, its path will be slightly different than when it arrived, carrying the gravitational signature of its encounter with our sun and planets into interstellar space. Consider what it means for an object to maintain its trajectory through interstellar space for millions of years. There are no course corrections, no navigation systems, no way to avoid obstacles or seek out destinations. 3i Atlas is purely at the mercy of gravity and momentum, following the laws of physics with perfect fidelity. Its path is deterministic in principle, meaning that if we knew the position and velocity of every star in the galaxy, we could calculate exactly where it came from and where it's going. But in practice, such calculations are impossible, and the object's past and future remain shrouded in uncertainty. The speed at which 3i Atlas is moving through our solar system also affects how we observe it, because it's moving so fast relative to Earth. Its position in the sky changes noticeably from night to night. Astronomers have to constantly update their telescope's pointing coordinates to keep track of it. This rapid apparent motion is another signature of its interstellar nature, distinguishing it from the more leisurely movements of solar system objects. It's like watching a jet plane cross the sky compared to watching a distant bird. The speed itself tells you something about what you're observing. The inclination of 3i Atlas's orbit, the angle at which it's tilted relative to the plane of our solar system, provides another clue about its origins. Most objects that formed in our solar system orbit roughly in the same plane, like marbles rolling on a flat table. But 3i Atlas is approaching from a significantly different angle, like a marble dropped onto the table from above. This high inclination is consistent with an object that originated elsewhere, approaching our solar system from a random direction in three-dimensional space. As we track 3i Atlas's path through our solar system, we're also tracking it through time. Light takes time to travel, so when we observe the object, we're seeing it as it was minutes or hours ago, depending on its distance. This time delay means that determining its precise position and velocity requires careful calculations, accounting for the finite speed of light. It's a reminder that in astronomy, we're always looking into the past even when observing objects in our own solar system. The path of 3i Atlas also intersects with the paths of human spacecraft, at least in a conceptual sense. We have sent probes to explore our solar system, and a few of them, like the Voyager spacecraft, are now heading into interstellar space themselves. In millions of years, these spacecraft will be interstellar objects in some other star system, assuming they survive the journey. There's a beautiful symmetry in this. As we receive visitors from other star systems, we're also sending out our own ambassadors, creating a slow exchange of objects across the galaxy. But the timescales involved in such exchanges are almost incomprehensible. If one of our Voyager spacecraft were to reach another star system and be detected by astronomers there, it would be millions of years from now. The civilization that detects it might have no connection to us, might not even be the same species that launched it. Similarly, if 3i Atlas was deliberately launched by another civilization, which seems unlikely but not impossible, that civilization might be long extinct. Their star might have died. Their planets might be frozen or vaporized. The object would be a message from the dead, an artifact of a vanished culture drifting through space. The statistical implications of detecting 3i Atlas are fascinating to consider. If such objects are passing through our solar system regularly, which seems likely given that we've detected several in just a few years of looking, then interstellar space must be populated with an enormous number of wandering objects. Some estimates suggest there could be more interstellar objects in our galaxy than there are stars, a vast population of cosmic nomads drifting between stellar systems. Most of these objects are too small or too distant for us to detect, passing through our neighborhood unseen and unrecorded. This hidden population of interstellar objects might play important roles in the galaxy's evolution. They could transfer materials between star systems, seeding young planetary systems with complex molecules or even microscopic life. They could influence the formation of planets by adding extra mass to protoplanetary disks. They could carry information about conditions in distant parts of the galaxy, serving as natural probes of regions we can't directly observe. In this view, objects like 3i Atlas are not isolated curiosities, but part of a vast, slow circulation system that connects all the star systems in our galaxy. The path that brought 3i Atlas to us was not inevitable, but the result of countless chance encounters and near misses. If its trajectory had been slightly different when it left its home system, it might never have come close enough to our Sun for us to detect it. If it had passed through a dense molecular cloud at some point in its journey, drag from the gas and dust might have slowed it down or altered its course. If it had passed close to a massive star or a black hole, gravitational effects might have flung it in a completely different direction. The fact that it arrived here, now, when we have the technology to detect it, is a cosmic coincidence of extraordinary proportions. Yet this coincidence is also a window of opportunity. For a brief time, measured in years rather than the millions of years of its journey, we have the chance to study this interstellar visitor. Every observation we make, every spectrum we collect, every measurement of its position and brightness adds to our understanding not just of this one object, but of the broader population of interstellar wanderers. We're learning how to find them, how to track them, how to extract the maximum amount of information from their brief passages through our neighborhood. The future path of 3I Atlas is as interesting as its past. After it leaves our solar system, it will return to the cold darkness of interstellar space, its brief warming by our sun just a fleeting episode in its vast journey. It will continue to wander through the galaxy, perhaps for billions more years, occasionally passing through other star systems, most of which will be empty of observers to notice its passage. Its ultimate fate might be to collide with a planet or a star, to be captured by a stellar system with just the right gravitational configuration, or to continue wandering until the galaxy itself evolves beyond recognition. In contemplating the path of 3I Atlas, we're also contemplating the paths of all things in the universe. Everything is in motion, from the smallest particles to the largest galaxy clusters. Nothing is truly at rest. Everything is travelling through space and time on its own trajectory. Our Earth orbits the Sun, our Sun orbits the galaxy. Our galaxy moves through the local group, and the local group itself is being pulled toward the great attractor, a gravitational anomaly hundreds of millions of light years away. In this cosmic dance, 3I Atlas is just one dancer among countless others, its path intersecting briefly with ours before continuing on its way. The mathematical beauty of orbital mechanics, which governs the path of 3I Atlas, is one of humanity's great intellectual achievements. From Newton's laws of gravitation to Einstein's general relativity, we've developed frameworks that allow us to predict and understand the motions of objects across the cosmos. These same laws that describe how an apple falls from a tree also describe how 3I Atlas falls through the galaxy. There's a profound unity in this, a demonstration that the universe operates according to consistent, comprehensible principles that we can discover and apply. Chapter 3. A Faint and Distant Light. In this chapter, we focus on the first gentle glimpses of 3I Atlas, those initial photons that travelled across the vast emptiness to reach our telescopes and announce the presence of this cosmic wanderer. Light, that fundamental messenger of the universe, carries within its wavelengths and intensities a wealth of information about its source. When we observe 3I Atlas, we're not just seeing a point of light moving against the stars. We're reading a complex message written in the language of photons, each one telling us something about the object's composition, its surface properties, its temperature, and perhaps even its history. The detection of 3I Atlas began not with a dramatic moment of discovery, but with the patient accumulation of data, night after night, as automated telescopes scan the sky in their endless vigil. These modern sentinels of the night use sophisticated cameras that can detect light far fainter than what our eyes can see, capturing photons that have travelled for years across space to reach us. When 3 Atlas first appeared in these images, it was nothing more than a faint smudge, barely distinguishable from the background noise of distant stars and galaxies. Yet within that faint smudge was encoded the story of an interstellar journey spanning millions of years. The brightness of 3I Atlas, or rather its faintness, tells us immediately that this is not a large object. If it were the size of a major asteroid or a small moon, it would be much brighter at its current distance. Instead, its dim appearance suggests something perhaps only a few kilometers across, maybe less. This small size makes its detection all the more remarkable. We're seeing something no bigger than a mountain that has travelled from another star system, a cosmic pebble that has crossed the vast ocean of interstellar space to wash up briefly on our shores. But the faintness of 3I Atlas also tells us something about its surface. Dark objects reflect less light than bright ones, and the amount of light reflected, what astronomers call the albedo, can reveal the composition of the surface. If 3I Atlas has a very low albedo, meaning it reflects very little of the sunlight that strikes it, this could indicate a surface covered in dark, carbon-rich materials. These organic compounds, as they're called, though they have nothing to do with life necessarily, are common in the outer reaches of our solar system and are thought to be primordial materials left over from the formation of planets. The colour of the light from 3I Atlas provides another layer of information. By carefully measuring how bright the object appears through different filters, astronomers can determine its colour, which in turn hints at its composition. Red surfaces might indicate the presence of certain organic molecules or weathered minerals. Blue surfaces might suggest fresher, less processed materials. Grey or neutral colours might indicate a mixture of different materials or a surface that has been heavily processed by cosmic radiation. Each subtle variation in colour is a clue, a piece of the puzzle that helps us understand what this object is made of and what it has experienced. Consider the journey of a single photon from the Sun to 3i Atlas, and then to our telescopes. This photon, created in the nuclear furnace at the Sun's core, takes thousands of years to work its way to the solar surface, bouncing between atoms in a random walk through the solar interior. Once it escapes into space, it travels at the speed of light, taking minutes or hours to reach 3i Atlas, depending on the object's distance. When it strikes the surface of 3i Atlas, most of its energy is absorbed, warming the surface imperceptibly, but a small fraction is reflected, beginning another journey through space, this time toward Earth. This reflected photon carries information about its encounter with 3i Atlas. Its wavelength might have shifted slightly, its polarization might have changed, its intensity diminished. These changes, subtle as they are, encode information about the surface it bounced off of. When this photon finally reaches our telescope, perhaps hours after leaving 3i Atlas, it contributes its tiny bit of information to our growing understanding of this interstellar visitor. Millions of such photons, collected over time, build up a picture of what we're seeing. The spectrum of light from 3i Atlas, if we can measure it precisely enough, is like a fingerprint of its composition. Different materials absorb and reflect light at different wavelengths, creating characteristic patterns that astronomers can recognize. Water ice has certain spectral features. Various minerals have others. Organic molecules have their own unique signatures. By spreading out the light from 3i Atlas into its component wavelengths, like a prism creating a rainbow, astronomers can search for these signatures, identifying what materials might be present on its surface. But obtaining a spectrum of such a faint object is challenging. It requires large telescopes, sensitive instruments, and often many hours of observation time. The light from 3i Atlas must be carefully separated from the background light of the sky, from nearby stars, from the glow of Earth's atmosphere. It's like trying to hear a whisper in a noisy room, requiring sophisticated techniques to extract the signal from the noise. Yet when successful, these spectroscopic observations can reveal remarkable details about an object billions of kilometers away. The way 3i Atlas's brightness changes over time, what astronomers call its light curve, provides information about its rotation and shape. As an irregularly shaped object tumbles through space, it presents different faces to the Sun and to us, causing its brightness to vary. These variations, measured precisely over many hours or days, can reveal how fast the object is rotating, whether it's tumbling chaotically or spinning stably, and give hints about its overall shape. Is it elongated like a cigar, flattened like a pancake, or roughly spherical like a lumpy potato? Each shape tells a different story about how the object formed and what forces have acted upon it. The phase function of 3i Atlas, how its brightness changes as the angle between the Sun, the object and Earth changes, provides yet another piece of information. Different surface textures scatter light in different ways. A smooth surface might create a sharp spike in brightness when the angles are just right, like a mirror flash. A rough surface might scatter light more evenly in all directions. By observing how the brightness of 3i Atlas changes as it moves through our solar system, changing the viewing geometry, astronomers can infer properties of its surface texture at scales too small to directly observe. The infrared light from 3i Atlas, if we can detect it, tells us about its temperature. All objects emit thermal radiation based on their temperature, with colder objects emitting at longer infrared wavelengths. By measuring this thermal emission, astronomers can determine how warm 3i Atlas is, which in turn depends on how much sunlight it absorbs versus how much it reflects, and how quickly it rotates. These thermal measurements can reveal whether the object has significant thermal inertia, whether it holds heat like a rock or loses it quickly like a pile of dust. The polarization of light from 3i Atlas provides still another dimension of information. When light reflects off a surface, it can become polarized, with the light waves aligned in a particular direction. The degree and angle of polarization depend on the composition and texture of the surface, as well as the viewing geometry. By measuring the polarization of light from 3i Atlas, astronomers can gain insights into its surface properties that wouldn't be apparent from brightness or color measurements alone. Think about what it means that we can extract all this information from such a faint point of light. 3 Atlas appears in our telescopes as nothing more than a dim dot, indistinguishable to the eye from countless background stars. Yet through careful observation and analysis, we can determine its size, its rotation rate, its surface composition, its temperature, and more. It's a remarkable demonstration of how much information is encoded in light, if only we know how to read it. The faintness of the 3i Atlas also means that we're pushing our instruments to their limits. Every observation is a battle against noise, against the random fluctuations that can overwhelm faint signals. Astronomers must carefully calibrate their instruments, account for atmospheric effects, remove cosmic ray hits, and apply sophisticated data processing techniques to extract meaningful measurements. It's a testament to human ingenuity and persistence that we can learn anything at all about such a faint, distant object. The discovery images of 3i Atlas show it as just a few pixels of light, moving slowly against the background stars. To the untrained eye, these images might seem unremarkable, even boring. But to astronomers, they're filled with excitement and possibility. Each pixel represents photons that have traveled from another star system, carrying information about conditions in a place we'll never be able to visit. Each observation adds to our understanding, building up a picture of this interstellar visitor one photon at a time. The color of 3i Atlas might also tell us about space weathering, the slow alteration of surfaces exposed to the harsh environment of space. In our solar system, we've observed that surfaces exposed to cosmic rays and solar wind particles gradually darken and redden over time. If 3i Atlas shows similar colors, it might indicate that space weathering operates similarly in interstellar space, or it might mean the object has spent time in the outer reaches of its original solar system before being ejected. Each possibility has different implications for the object's history and composition. As our telescopes track 3i Atlas night after night, we're also tracking changes in its appearance. Is it developing a coma, a fuzzy envelope of gas and dust that would indicate it's releasing volatile materials as it warms? Are there jets or outbursts that might reveal active regions on its surface? These changes, if they occur, would provide dynamic information about the object's composition and structure, showing us not just what it is, but how it responds to the warming influence of our Sun. The challenge of observing 3 Atlas is compounded by its motion across the sky. Unlike distant stars and galaxies, which appear fixed in position, 3i Atlas moves noticeably from night to night. Telescopes must track this motion precisely to build up enough light for detailed observations. It's like trying to photograph a moving car at night with a long exposure. Any error in tracking will blur the image and lose precious information. The faintness of 3i Atlas also raises questions about what we might be missing. If this object, perhaps a few kilometers across, is barely detectable with our best telescopes, how many smaller interstellar objects are passing through our solar system completely unnoticed? There might be a vast population of meter-sized or even smaller interstellar particles constantly streaming through our neighborhood, invisible to our current instruments. 3i Atlas might be just the tip of an enormous iceberg, the largest and brightest member of a population we're only beginning to discover. The spectral features we search for in the light from 3i Atlas are like words in an alien language we're trying to decipher. The absorption line of water ice at certain wavelengths, the spectral slope that indicates organic molecules, the mineral features that suggest silicates or metals, Each of these is a word that helps us understand what story this object is telling, but the language is complex and often ambiguous. The same spectral feature might be produced by different materials under different conditions, requiring careful analysis and often complementary observations to interpret correctly. The light from 3i Atlas has another remarkable property. It's old light in a sense. The photons we're detecting left the Sun hours ago, reflected off 3i Atlas, and then travelled to Earth. During that time, 3i Atlas has continued to move, the Earth has rotated, our telescope has tracked across the sky. We're always seeing 3i Atlas as it was, not as it is, a reminder that all astronomical observation is a form of time travel, looking into the past even when observing objects in our own solar system. The challenge of extracting meaningful information from such faint light has driven technological innovation in astronomy. Better detectors, more sophisticated data processing algorithms, larger telescopes, all have been developed partly in response to the challenge of observing ever fainter objects. 3i Atlas and objects like it are pushing us to improve our capabilities, to see fainter, to measure more precisely, to extract more information from every precious photon we collect. Consider the remarkable fact that we can determine the surface composition of an object billions of kilometers away by analyzing its light. We can't touch 3i Atlas, we can't bring samples back to Earth for analysis, and we can't land a probe on its surface. Yet through the careful analysis of its reflected and emitted light, we can determine what it's made of, how it's structured, how it's responding to its environment. It's a form of remote sensing that would seem like magic to earlier generations, yet it's based on solid physical principles and careful observation. The faint light from 3i Atlas also connects us to the broader universe in a profound way. The same physical laws that govern how light interacts with matter here on Earth apply to this interstellar visitor. The same quantum mechanical principles that determine how atoms and molecules absorb and emit light operate throughout the cosmos. By studying the light from 3i Atlas, we're confirming the universality of physical laws, demonstrating that science works the same way in interstellar space as it does in our laboratories. As we observe 3i Atlas, we're also observing the limitations of our current technology. There are measurements we'd like to make but can't, details we'd like to resolve but can't see, questions we'd like to answer but don't have the data for. These limitations are frustrating but also motivating. They tell us what we need to work on, what new instruments we need to build, what new techniques we need to develop. In this way, 3i Atlas is not just teaching us about interstellar objects, it's teaching us about ourselves, about our capabilities and our limitations. The photons from 3i Atlas that reach our telescopes have survived an incredible journey. They've avoided being absorbed by interstellar dust. They've maintained their path across billions of kilometers of space. They've passed through Earth's atmosphere without being scattered or absorbed. Each photon that successfully completes this journey and is detected by our instruments is a small miracle, a messenger that has overcome enormous odds to deliver its tiny packet of information about this interstellar visitor. The analysis of light from 3i Atlas is a collaborative effort involving astronomers around the world. Observations from different telescopes are combined, measurements from different instruments are compared, interpretations from different research groups are debated. This collaboration is essential because no single telescope or team can gather all the necessary data. The faintness of 3i Atlas requires us to work together, pooling our resources and expertise to extract the maximum amount of science from this rare opportunity. As 3i Atlas continues its journey through our solar system, the quality of light we receive from it is changing. As it moves closer to or farther from the Sun, its illumination changes. As it moves closer to or farther from Earth, its apparent brightness changes. As the viewing geometry evolves, different aspects of its surface and structure are revealed. This dynamic situation means that patient, continued observation can reveal details that wouldn't be apparent from a single snapshot. The story of 3i Atlas is being written in light, and we need to keep reading to understand the full narrative. The faint light from 3i Atlas also reminds us of the vastness of space and the rarity of matter within it. This object, perhaps containing more mass than a mountain, is just a tiny speck in the enormous volume of our solar system, which itself is just a tiny speck in the galaxy. The fact that we can detect it at all, that enough photons reach us to form an image and take measurements, is remarkable. It's a reminder that even in the vast emptiness of space, there are stories to be found, messages to be decoded, wonders to be discovered, if only we have the patience and skill to look for them. As we prepare to delve deeper into what this faint light might be telling us about the composition and history of 3i Atlas, we carry with us an appreciation for the remarkable chain of events that allows us to study this object at all. From the nuclear fusion in our sun that creates the photons, to the journey of those photons to 3i Atlas, to their reflection and journey to Earth, to their detection by our instruments and analysis by our computers and minds. It's an extraordinary process that connects us to a visitor from another star system. In the faint light of 3i Atlas, we see not just an interstellar object, but a bridge between our solar system and the wider galaxy, a tangible connection to the cosmos beyond our local neighborhood. The faint light from 3i Atlas carries within it not just information about the object itself, but whispers of an ancient sun, a star we will never see, around which this cosmic wanderer might have been born billions of years ago. Let your mind drift now as we journey backward through time and space, imagining the stellar cradle where our visitor began its existence. Was it a young, hot blue star burning through its nuclear fuel at a prodigious rate, flooding its system with intense ultraviolet radiation? Or perhaps it was born around a calm, ancient red dwarf, one of those patient stars that can shine steadily for trillions of years, outlasting nearly everything else in the universe. Each type of star would leave its own unique signature on the objects that formed around it, like a parent's features reflected in their children's faces. When we think about the parent star of 3i Atlas, we're engaging in a form of cosmic archaeology, trying to reconstruct an entire solar system from a single surviving fragment. It's like finding a single pottery shard and trying to imagine the civilization that created it, the hands that shaped it, the kiln that fired it, the home where it was used. The task seems impossible, yet every detail we can observe about 3i Atlas provides a clue, a constraint on what its original environment might have been like. The chemical composition tells us about the materials available in that ancient protoplanetary disk. The isotopic ratios hint at the nuclear processes that created those materials. The structure and density suggest the conditions under which the object formed. Imagine, if you will, a star being born somewhere in our galaxy millions or billions of years ago. In a vast molecular cloud, a region of slightly higher density begins to collapse under its own gravity. As it collapses, it spins faster, like a figure skater pulling in their arms, and flattens into a disk. At the center, the temperature and pressure rise until nuclear fusion ignites, and a new star is born. Around this infant star, the leftover material in the disk begins to clump together, forming planetesimals, the building blocks of planets. In this swirling disk of gas and dust somewhere, the materials that would become 3i Atlas are coming together, grain by grain, molecule by molecule. The type of star at the center of this forming system would profoundly influence everything that formed around it. A massive, hot star would blast its surroundings with intense radiation, driving away lighter elements like hydrogen and helium, leaving behind only the heavier, more refractory materials. Objects forming in such a system would be rich in metals and silicates, but poor in volatile compounds. The stellar wind from such a star would be powerful, potentially stripping away the atmospheres of forming planets, sculpting and modifying everything in its vicinity. If 3i Atlas formed in such an environment, it would bear the scars of that intense stellar bombardment, its surface and composition shaped by forces far more powerful than anything in our own, more sedate solar system. On the other hand, if 3i Atlas formed around a cooler, smaller star, the story would be very different. Red dwarf stars, which make up the majority of stars in our galaxy, create much gentler environments for planet formation. Their habitable zones where liquid water could exist are much closer to the star, and their stellar winds are typically weaker. Objects forming in the outer regions of such systems could retain significant amounts of volatile materials, water ice, methane, ammonia, compounds that would be blown away in hotter stellar environments. The lower ultraviolet radiation from red dwarfs might also allow more complex organic molecules to survive on or near the surfaces of forming objects. Consider too the metallicity of the parent star, astronomers' term for the abundance of elements heavier than hydrogen and helium. Stars that formed early in the galaxy's history had very low metallicity because there hadn't been time for many generations of stars to create and disperse heavy elements through supernovae. Objects forming around such metal-poor stars would have very different compositions than those forming around younger, metal-rich stars like our Sun. If 3I Atlas came from an old metal-poor star, it might contain primarily hydrogen and helium compounds, with only trace amounts of heavier elements. This would make it fundamentally different from objects in our solar system, a relic from a time when the galaxy itself was chemically younger. The location within its original solar system where 3I Atlas formed would also leave indelible marks on its composition and structure. If it formed close to its parent star inside what we call the frost line, it would be primarily rocky, composed of materials that could remain solid at high temperatures. But if it formed farther out, beyond the frost line, it could be rich in ices, not just water ice but frozen methane, ammonia, carbon dioxide and other compounds that can only condense in the cold outer reaches of a stellar system. The exact location of this frost line would depend on the luminosity of the parent star, creating a unique geography of composition for each stellar system. The age of the parent star when 3I Atlas was ejected also matters enormously. Young stars are often surrounded by disks of gas and dust from which planets are still forming. They may be members of stellar clusters, regions where many stars are born together from the same molecular cloud. In such environments, gravitational interactions between stars can be common, potentially disrupting planetary systems and ejecting objects into interstellar space. If 3I Atlas was ejected early in its history, it might preserve very primitive materials, samples from the earlier stages of planet formation. But if it was ejected later, after spending billions of years in its original system, it might show signs of processing, of chemical and physical evolution within that system. The mechanism by which 3I Atlas was ejected from its original system also connects to the nature of its parent star. If the star had a binary companion, another star orbiting nearby, the gravitational dynamics would be complex and chaotic. Binary star systems, which are actually more common than single stars like our Sun, can easily eject objects through gravitational interactions. The two stars act like a gravitational slingshot, potentially launching objects at high speeds into interstellar space. If this was the case for 3I Atlas, its ejection velocity and direction would carry information about the orbital configuration of that binary system. Alternatively, 3I Atlas might have been ejected by a close encounter with a giant planet in its original system. Jupiter-like planets, through their immense gravity, can scatter smaller objects, sometimes ejecting them entirely from the system. This process, called gravitational scattering, is thought to be responsible for shaping the architecture of many planetary systems. If 3I Atlas was ejected this way, it might have come from a system with giant planets, perhaps arranged differently than in our solar system. The violence of such an ejection might have left physical marks on the object, fractures or deformations that we might be able to detect. There's also the possibility that 3I Atlas witnessed the death of its parent star. If that star was massive enough, it might have ended its life in a supernova explosion, a catastrophic event that would have destroyed any nearby planets and ejected any surviving objects at enormous speeds. The surface of 3 Atlas, if it experienced such an event, might show unique signatures of exposure to the intense radiation and particle flux from a supernova. Certain isotopes might have been created by the neutron bombardment, leaving radioactive traces that would slowly decay over millions of years. These would be like timestamps, allowing us to determine when the supernova occurred. If the parent star was more like our Sun, destined to end its life as a white dwarf, 3I Atlas might have been ejected during the star's red giant phase. As stars like the Sun near the end of their lives, they expand enormously, potentially engulfing inner planets and dramatically altering the orbits of outer objects. The stellar wind during this phase becomes much stronger, potentially stripping away the atmospheres and even surfaces of nearby objects. If 3I Atlas experienced this stellar death throes, it might show signs of severe thermal processing. Its surface melted and reformed by the intense heat of the expanding star. The chemical abundance patterns in 3I Atlas, if we could measure them precisely, would be like a fingerprint of its parent star. Different stars have slightly different ratios of elements, depending on their mass, age, and the environment in which they formed. These abundance patterns are passed on to the objects that form around them. By comparing the chemical fingerprint of 3I Atlas to stars in our galaxy, we might be able to identify candidates for its parent star, or at least narrow down the type of star it came from. It's like analysing someone's DNA to determine their ancestry, except we're doing it for a cosmic traveller. The magnetic field of the parent star would also have influenced the formation and evolution of 3I Atlas. Young stars often have powerful magnetic fields that can channel charged particles, creating intense radiation belts similar to but much stronger than the Van Allen belts around Earth. Objects forming in such environments would be subjected to constant particle bombardment, which could alter their surface chemistry and create unique mineral formations. The magnetic field could also influence where and how objects could form in the protoplanetary disk, creating regions where formation was enhanced or suppressed. Consider the stellar neighbourhood where 3I Atlas's parent star resided. Was it in a dense stellar cluster, where interactions with other stars were common? Was it in a spiral arm of the galaxy, where star formation is active and supernovae are frequent? Or was it in the galactic halo, where stars are older and more isolated? Each environment would provide different conditions for planet formation and evolution. In dense stellar regions, radiation from nearby massive stars could influence the chemistry of protoplanetary disks. Supernovae could inject fresh radioactive materials. Close stellar encounters could disrupt forming planetary systems. All of these environmental factors would leave their marks on objects like 3I Atlas. The rotation rate of the parent star might also have influenced 3I Atlas. Stars rotate at different rates, and this rotation can affect the distribution of material in the protoplanetary disk. Rapidly rotating stars might have disks that extend farther from the star, allowing objects to form at greater distances. The stellar rotation could also generate stronger magnetic fields and stellar winds, influencing the composition and structure of forming objects. If we could somehow determine the original rotation rate of 3I Atlas itself, it might provide clues about the rotation of its parent star and the dynamics of its original system. The metallicity gradient within the galaxy adds another layer to this cosmic detective story. The inner regions of our galaxy tend to have higher metallicity than the outer regions, because star formation and stellar death have been more active there for longer. If 3I Atlas came from the inner galaxy, it might be more metal-rich than if it came from the outer regions. This metallicity gradient has evolved over time, so the composition of 3I Atlas might also tell us something about when it formed, adding a temporal dimension to our spatial understanding of its origins. Imagine the last days of 3I Atlas in its original system, before it was ejected into interstellar space. Perhaps it was a comet in that system's Oort cloud, orbiting peacefully for billions of years until a passing star disturbed its orbit. Or maybe it was an asteroid in an inner belt, minding its own business until a migrating giant planet scattered it outward. The final gravitational interaction that sent it on its interstellar journey might have been sudden and violent, or it might have been a gradual process, a series of small perturbations that eventually added up to escape velocity. Each scenario would result in different ejection velocities and potentially different physical states for the object. The possibility that 3I Atlas might carry information about extinct radioactive isotopes is particularly intriguing. In the early solar system, short-lived radioactive isotopes like aluminum-26 played important roles in heating and processing materials. These isotopes, produced in supernovae and stellar winds, decay relatively quickly on cosmic timescales. If 3I Atlas formed when such isotopes were present in its parent system, the decay products might still be detectable, providing a clock that tells us when the object formed. It's like finding a stopped watch at a crime scene. Even though it's no longer running, it tells you when something important happened. The stellar wind from the parent star would have been a constant presence during 3I Atlas's formation and early evolution. This stream of charged particles flowing outward from the star would have interacted with any magnetic fields in the forming object, potentially creating complex electromagnetic phenomena. The stellar wind might have implanted ions into the surface layers, creating a record of the star's composition and activity. Over time, these implanted materials would have been buried by continued accretion or modified by space weathering, but traces might still remain, especially in protected interior regions. If the parent star had unusual properties, such as being a variable star with periodic brightness changes, this might have created unique conditions for planet formation. The varying stellar radiation could have created cycles of heating and cooling in the protoplanetary disk, potentially leading to layered structures in forming objects. Imagine 3I Atlas as a cosmic tree ring, with each layer recording a period of its parent star's variability. While we likely can't resolve such fine structure, the overall composition might still reflect these unusual formation conditions. The question of whether 3I Atlas's parent star had habitable planets is a fascinating one to contemplate. If that system harbored life at some point, could there be any connection to 3I Atlas? Not life itself, certainly, as the object has been travelling through the freezing void for millions of years, but perhaps organic molecules created by that life, or even just the chemical precursors that might have led to life, could be preserved in this cosmic time capsule. It's an extremely remote possibility, but the mere fact that we can consider it shows how objects like 3I Atlas connect us to the broader question of life in the universe. The parent star of 3I Atlas might still exist, continuing to shine somewhere in our galaxy, unaware that one of its children has wandered so far from home. Or it might be long dead, reduced to a white dwarf, a neutron star, or dispersed entirely in a supernova explosion. If we could somehow identify this star, it would be like finding the birthplace of a message in a bottle, allowing us to understand the full context of 3I Atlas's story. But the galaxy is vast, containing hundreds of billions of stars, and the chances of identifying one specific star as the parent of 3I Atlas are essentially zero with our current technology. As we contemplate the ancient sun that gave birth to 3I Atlas, we're reminded of the deep connections between all stars and their offspring. Every atom heavier than hydrogen in 3I Atlas was forged in the nuclear furnace of a star, either its parent star or earlier generations of stars. The calcium, iron, silicon, carbon, and other elements that make up this object are the ashes of stellar fires, assembled and reassembled over billions of years of cosmic evolution. In studying 3I Atlas, we're studying the products of stellar nucleosynthesis, the process by which stars create the elements that make up planets, and ultimately, life itself. The very fact that we can speculate about the parent star of 3I Atlas, that we can construct plausible scenarios for its origin and evolution, is a testament to how much we've learned about star and planet formation. A century ago, we didn't even know that other galaxies existed. Now we're analysing visitors from other star systems, trying to reconstruct their histories, attempting to understand the diversity of planetary systems throughout our galaxy. It's a remarkable progression of knowledge, and objects like 3i Atlas are pushing us to expand that knowledge even further. Now we arrive at the heart of our mystery, the tantalizing possibility that 3i Atlas might be carrying within its frozen interior a message from the deep past, a time capsule that could rewind our understanding of cosmic history. What if this interstellar wanderer contains pristine materials from the dawn of another solar system, preserved like ancient insects in amber, waiting billions of years for someone to discover and decode their secrets? The idea that we might be looking at a fragment of another world's beginning, frozen at a moment in time before planets formed, before life emerged, perhaps before our own sun was even born, fills the mind with a sense of wonder that transcends scientific curiosity and touches something deeper in our cosmic consciousness. When we speak of 3i Atlas potentially rewinding history, we're not talking about time travel in the science fiction sense, but something perhaps even more profound. This object might preserve within its structure a record of conditions in the galaxy billions of years ago, when the chemical composition was different, when the rate of star formation was different, when the entire cosmic environment was younger and more chaotic. Every molecule within 3i Atlas, every grain of dust, every crystal of ice, is a data point in this vast historical record, waiting to be read if only we knew the language. Consider what it means for an object to remain essentially unchanged for millions or billions of years. Here on Earth, everything is in constant flux. Mountains rise and erode away. Oceans evaporate and refill. Even the continents themselves drift across the planet's surface. The oldest rocks on Earth are about 4 billion years old, and they've been heavily altered by geological processes. But 3i Atlas, drifting through the cold vacuum of interstellar space, has been in a state of near-perfect preservation. The temperature just a few degrees above absolute zero means that chemical reactions essentially stop. The absence of liquid water means no dissolution or recrystallization. The vacuum means no oxidation or other atmospheric interactions. It's the ultimate deep freeze, preserving materials in their original state far better than any museum or archive on Earth ever could. The possibility that 3i Atlas contains water ice is particularly intriguing when we think about rewinding history. Water is one of the most abundant compounds in the universe, formed when hydrogen, the most common element, combines with oxygen, produced in the cores of massive stars. But not all water is the same. The ratio of heavy water containing deuterium instead of regular hydrogen to normal water can tell us about the conditions under which the water formed. Temperature, pressure, radiation environment all leave their signatures in this isotopic ratio. If 3i Atlas contains water ice with isotopic ratios different from what we see in our solar system, it would be direct evidence of formation under different conditions, a glimpse into another chapter of cosmic history. But water is just the beginning. The real treasure might be organic molecules, those complex carbon-based compounds that are the building blocks of life as we know it. In the cold of interstellar space, protected from destructive radiation by layers of ice and dust, complex organic molecules could survive for enormous periods of time. These molecules might include amino acids, the building blocks of proteins or nucleotides, the components of DNA and RNA. They might include sugars, lipids, or other compounds essential to biological processes. If such molecules exist within 3i Atlas, they wouldn't be evidence of life, but they would be evidence of the chemical processes that could lead to life, preserved from another place and time. The formation of organic molecules in space is a fascinating process that we're only beginning to understand. In the cold, dark molecular clouds where stars form, simple molecules can stick to dust grains, forming icy mantles. When these grains are exposed to ultraviolet radiation or cosmic rays, the energy can drive chemical reactions that would never occur under normal conditions. Atoms and molecules can be broken apart and recombined in new ways, creating increasingly complex compounds. This process, called cosmic chemistry or astrochemistry, can produce a remarkable variety of organic molecules, from simple compounds like methanol to complex ones like glycine, the simplest amino acid. If 3I Atlas formed in such a molecular cloud, or if it spent time passing through one during its interstellar journey, it might have accumulated a rich inventory of organic molecules. These wouldn't be biological in origin, but they would be the kinds of molecules that could, under the right conditions, lead to the emergence of life. Finding such molecules in an interstellar object would tell us that the ingredients for life are not unique to our solar system, but are produced naturally throughout the galaxy. It would be a profound statement about the potential for life elsewhere in the universe. The idea of panspermia, that life or its precursors could be spread between star systems by wandering objects like 3I Atlas, becomes more plausible when we consider the object as a potential carrier of organic molecules. While the transfer of actual living organisms seems unlikely given the harsh conditions and enormous timescales involved, the transfer of complex organic molecules is entirely possible. These molecules, delivered to a young planet by impacting comets or asteroids, could jumpstart the chemical evolution that leads to life. In this view, 3I Atlas and objects like it are not just passive wanderers, but active participants in the cosmic distribution of the ingredients for life. The preservation of materials within 3I Atlas might extend beyond molecules to include microscopic structures that could tell us about the physical processes in its original solar system. For instance, certain types of mineral grains called pre-solar grains are known to preserve isotopic signatures from specific stellar environments. These grains, formed in the atmospheres of dying stars or in supernova explosions, can survive incorporation into new solar systems. If 3I Atlas contains pre-solar grains from its parent system, or even from earlier generations of stars, they would be like individual letters in a cosmic message, each one telling us about specific stellar processes and environments. The concept of rewinding history also applies to the magnetic fields that might be recorded within 3I Atlas. Some materials can preserve a record of the magnetic fields they experienced when they formed or were last heated. This paleomagnetic record, as it's called, could tell us about the magnetic environment in 3I Atlas's original solar system. Was the parent star magnetically active? Were there strong magnetic fields in the protoplanetary disk? These magnetic records would be like fossilized compass needles, pointing back toward conditions that existed billions of years ago and billions of kilometers away. Consider the possibility that 3I Atlas contains materials that predate our own solar system. Our sun and planets formed about 4.6 billion years ago, but the galaxy is more than 13 billion years old. If 3I Atlas comes from an older stellar system, it might contain materials that formed when the galaxy itself was younger. When the cosmic environment was different, the rate of star formation was higher in the past, supernovae were more common, and the overall chemical composition of the galaxy was different. Materials formed under those conditions would carry signatures of that earlier epoch, allowing us to peer back into the galaxy's youth. The layered structure that might exist within 3I Atlas could preserve a chronological record of its history, like tree rings or geological strata. Different layers might have formed at different times or under different conditions. The innermost core might preserve the most primitive materials, those that first came together in the protoplanetary disk. Surrounding layers might record subsequent processing, impacts with other objects, or exposure to different environments. The outermost layer, the radiation mantle created during its interstellar journey, would be the most recent chapter in this long history. Reading these layers, if we could access them, would be like reading a book written over billions of years. The possibility that 3I Atlas might be a fragment of a disrupted planet adds another dimension to its potential as a historical record. If a planet in its original system was destroyed, perhaps by a giant impact or tidal disruption, 3I Atlas might be a piece of that planet's interior. This would give us access to materials that were processed in a planetary environment, subjected to the heat and pressure of a planetary interior, perhaps even differentiated into core, mantle, and crust. Finding such materials in an interstellar object would provide unprecedented insights into planet formation and evolution in other stellar systems. The chemical gradients that might exist within 3I Atlas could tell us about the processes that formed and modified it. For instance, if volatile compounds are concentrated in the interior while the exterior is depleted, this might indicate that the object has been heated at some point, causing volatiles to migrate inward or escape entirely. Conversely, if certain elements are concentrated at the surface, this might indicate condensation from a gas phase or implantation by stellar winds. These chemical gradients would be like frozen snapshots of dynamic processes, preserving information about events that occurred long ago and far away. The role of 3I Atlas as a potential carrier of supernova products is particularly fascinating. When massive stars explode as supernova, they create and disperse heavy elements that can't be formed in any other way. These elements, including many that are essential for life, are scattered into space and eventually incorporated into new stars and planets. If 3 Atlas formed in a region enriched by a recent supernova, it might contain unusually high abundances of certain elements or isotopes. These supernova fingerprints would tell us not just about 3I Atlas's history, but about the stellar life and death cycles in its region of origin. The possibility that 3I Atlas might contain exotic materials not found in our solar system opens up intriguing possibilities. Different stellar environments can produce different minerals, different crystal structures, different chemical compounds. For instance, in the extreme conditions around certain types of stars, silicon carbide minerals can form that are rare or absent in our solar system. Finding such exotic materials in 3I Atlas would expand our understanding of the diversity of materials that can exist in planetary systems, showing us that our solar system's inventory is just one example of what's possible. The question of whether 3I Atlas might contain materials older than the galaxy itself might seem absurd, but it raises interesting points about cosmic recycling. The materials in any object have a history that extends back to the Big Bang. The hydrogen in 3I Atlas was formed in the first minutes after the Big Bang. The helium mostly dates from the same era. The heavier elements were formed in successive generations of stars, each one building on the ashes of its predecessors. In this sense, 3I Atlas is not just rewinding the history of its parent solar system, but carrying within it the entire history of matter in the universe. The preservation of noble gases within 3I Atlas could provide unique insights into its history. Noble gases like helium, neon, and argon don't form chemical compounds easily, so their abundances and isotopic ratios can remain unchanged for billions of years. Different processes produce different isotopes of these gases, so their ratios can fingerprint specific events or environments. Solar wind implantation produces one signature, cosmic ray interactions produce another, and radioactive decay produces yet another. The noble gas inventory of 3I Atlas, if we could measure it, would be like a detailed diary of its experiences. As we contemplate 3I Atlas as a potential time capsule, we're also confronting the limitations of our ability to read its contents. We can't land on this object. We can't bring samples back to Earth. We can't analyze it with the sophisticated instruments in our laboratories. We're limited to remote observations, to analyzing the light it reflects and emits. It's like trying to read a book through a frosted window, able to make out general shapes and colors, but missing the fine details. This limitation makes the information we can extract all the more precious, and drives us to develop better techniques for remote analysis. The concept of 3I Atlas rewinding history extends to its potential role in calibrating our models of galactic chemical evolution. Astronomers have developed sophisticated models of how the chemical composition of our galaxy has changed over time as successive generations of stars have created and dispersed heavy elements. But these models are based primarily on observations of stars and gas clouds, not solid objects. If we could determine the age and composition of 3I Atlas precisely, it would provide a unique data point for these models, a physical sample from another place and time that could confirm or challenge our understanding of galactic evolution. The possibility that 3i Atlas might contain materials processed by life, however remote, adds a philosophical dimension to our investigation. We're not suggesting that 3i Atlas carries alien microbes or fossils, but rather that if life existed in its parent system, it might have altered the chemistry of that system in subtle ways that could be preserved in this object. Life on Earth has profoundly altered our planet's chemistry, from the oxygen in our atmosphere to the deposits of limestone and other biological minerals. If similar processes occurred in 3i Atlas's parent system, traces might remain, though distinguishing biological from non-biological processes at such a remove would be extraordinarily challenging. The idea that 3i Atlas might be rewinding history also applies to our understanding of our own solar system. By providing an example of materials from another stellar system, it gives us a comparison point, a way to understand what's unique about our home and what's common throughout the galaxy. Are the materials in our solar system typical or unusual? Are the processes that formed our planets common or rare? These questions can only be answered by studying objects from other stellar systems, and 3i Atlas provides one of our first opportunities to do so. The thermal history recorded within 3i Atlas could tell us about every significant heating event it has experienced. When materials are heated, their crystal structures can change, their volatile compounds can be lost, and their isotopic ratios can be altered. Each heating event, whether from formation in a hot protoplanetary disk, impact with another object, or close passage by a star, would leave its mark. The current state of 3i Atlas represents the sum of all these thermal events, a palimpsest of heating and cooling that spans billions of years. If we could read this thermal history, we could reconstruct major events in the object's past, creating a timeline of its experiences. As our visitor draws nearer to our sun, it begins to change, to awaken from its long cosmic slumber. This transformation is not violent or dramatic, but slow and graceful, like a flower opening in extreme slow motion, revealing secrets that have been locked away for perhaps millions of years. The warming rays of our sun, feeble as they might seem at the vast distances where 3i Atlas travels, are nonetheless the most intense heat this object has experienced since it left its parent star system. This gentle warming is causing a metamorphosis, a gradual unfolding of the object's nature that provides us with a unique opportunity to witness the anatomy of an interstellar traveller. The process begins subtly, almost imperceptibly. As sunlight strikes the surface of 3i Atlas, it's absorbed by the dark materials that coat this cosmic wanderer. These materials, possibly complex organic compounds that have been created and modified by millions of years of cosmic ray bombardment, are excellent absorbers of radiation. They soak up the sun's energy like a black cloth on a summer day, warming ever so slightly. This warming might only amount to a few degrees, from the near absolute zero of interstellar space to something still profoundly cold by Earth standards. But it's enough to begin mobilizing molecules that have been frozen in place for eons. Consider what happens at the molecular level as this warming occurs. In the extreme cold of interstellar space, molecules are essentially motionless, locked in a crystalline embrace that can last indefinitely. But as temperature rises, even slightly, these molecules begin to vibrate. The vibrations grow stronger with increasing temperature, until some molecules have enough energy to break free from their crystalline prison. This process, called sublimation, allows solid materials to transform directly into gas without passing through a liquid phase, something that happens readily in the vacuum of space where liquid states are generally impossible. The first materials to respond to this warming are the most volatile compounds, those with the weakest molecular bonds. These might include carbon monoxide, methane, or nitrogen, substances that can sublimate at temperatures that would still freeze water instantly. As these molecules escape from the surface of 3i Atlas, they carry with them information about the object's interior composition, like breath revealing something about the body it comes from. Each escaping molecule is a messenger, carrying news of materials that have been sequestered since before our solar system existed. This sublimation process doesn't occur uniformly across the surface of 3I Atlas. The side facing the Sun warms more than the side facing away, creating temperature gradients that can drive complex processes. On the sunlit side, volatiles might be actively sublimating, while on the dark side, some of these same gases might be recondensing, creating a kind of atmospheric circulation even though the atmosphere is vanishingly thin. This process could be gradually changing the distribution of materials on the object's surface, creating compositional differences between the day and night sides that didn't exist during its interstellar journey. As 3I Atlas rotates, if indeed it does rotate, different areas of its surface are exposed to sunlight, creating a complex pattern of heating and cooling. Imagine the surface as a patchwork of different materials, each with its own thermal properties and sublimation temperatures. As the object turns, each patch experiences its own cycle of warming and cooling, sublimation and recondensation. This creates a dynamic surface environment, constantly changing on timescales of hours or days, a stark contrast to the static conditions that prevailed during the millions of years of interstellar travel. The gases released from 3I Atlas don't simply disappear into space. Initially, they form a thin envelope around the object, what astronomers call a coma when observed around comets. This coma, though incredibly tenuous by Earth standards, might extend for thousands or even millions of kilometers around the object. Within this ghostly shroud, complex chemistry can occur. Molecules broken apart by solar ultraviolet radiation can recombine in new ways. Dust particles lifted from the surface can serve as catalysts for chemical reactions. The coma becomes a natural laboratory where cosmic chemistry plays out in real time. The interaction between the solar wind and any gases released from 3I Atlas creates another layer of complexity. The solar wind, that stream of charged particles constantly flowing from our Sun, can ionize molecules in the coma, stripping away electrons and creating ions. These ions, being charged, respond to magnetic fields, both the Sun's and any that might be carried by the solar wind itself. This can create complex structures in the coma, including tail-like features that stream away from the Sun, always pointing away regardless of the object's direction of motion. If 3I Atlas develops such a tail, it would be made of materials from another star system, a cosmic pennant flying briefly in our solar wind. The dust released from 3I Atlas, if any is being released, tells its own story. These tiny particles, perhaps microscopic grains of silicates or carbon compounds, were likely formed in the protoplanetary disk of another star system. They've been locked in the ice of 3I Atlas for millions of years, preserved like ancient artifacts. Now liberated by sublimating gases, they drift away from the object, each grain following its own orbit around the Sun. The larger grains might follow paths similar to 3I Atlas itself, while the smallest ones might be blown out of the solar system entirely by radiation pressure from sunlight. This process of dust release could be revealing the object's internal structure in ways we couldn't observe otherwise. If 3I Atlas is a loosely bound collection of smaller particles, held together by ice that's now sublimating, we might be witnessing a gradual disintegration. Alternatively, if it has a solid core surrounded by more volatile materials, the sublimation might be revealing this core, stripping away the outer layers like an archaeological excavation in extreme slow motion. Each possibility would tell us something different about how objects form and evolve in other star systems. The spectroscopic signatures of the gases released from 3I Atlas are particularly valuable for understanding its composition. Different molecules absorb and emit light at specific wavelengths, creating spectral fingerprints that astronomers can identify. Water vapor has one signature, carbon dioxide another, methane yet another. By analyzing the spectrum of light from 3I Atlas and its coma, we can identify what molecules are being released and in what proportions. This is like performing a chemical analysis on materials from another star system, something that would have seemed impossible just a few decades ago. The rate at which materials are being released from 3I Atlas provides information about its structure and composition. A high rate of gas production might indicate a volatile, rich composition, while a low rate might suggest a more refractory, rock-like nature. Changes in the production rate as the object moves closer to or farther from the Sun tell us about the distribution of different materials within it. If the production rate varies with rotation, it might indicate that different areas of the surface have different compositions, or that there are active regions, specific spots where sublimation is particularly vigorous. The possibility that 3I Atlas might fragment as it warms is both exciting and concerning. Exciting because fragmentation would expose fresh, unprocessed interior materials that have been shielded from cosmic rays during the interstellar journey. Concerning because if the object breaks apart completely, we might lose the opportunity to study it as a coherent whole. Fragmentation events, if they occur, would be dramatic moments in the object's unfolding story, potentially releasing large amounts of gas and dust and creating multiple pieces that could be studied separately. The thermal stresses induced by the Sun's warming could be significant enough to crack or fracture 3I Atlas. As the surface warms and expands while the interior remains cold, differential thermal expansion could create stresses that exceed the material's strength. These thermal cracks might propagate deep into the object, creating pathways for volatiles to escape from the interior. The pattern of these cracks, if we could observe them, would tell us about the mechanical properties of the material, its strength, brittleness, and homogeneity. The color changes that might occur as 3I Atlas warms are another fascinating aspect of its unfolding mystery. Fresh surfaces exposed by sublimation or fragmentation might have different colors than the radiation-processed exterior. These color differences could help us distinguish between primordial materials and those altered during the interstellar journey. If the object becomes redder as it warms, it might indicate the presence of organic compounds. If it becomes bluer, it might suggest the exposure of water ice or other volatile ices. The interaction between different volatile species as they sublimate creates a complex situation. Some molecules might act as carriers for others, with the sublimation of one species facilitating the release of another. For instance, carbon dioxide sublimating from below a water ice layer might crack and lift the ice, exposing it to sunlight and accelerating its sublimation. These coupled processes create non-linear behaviors, where small changes in temperature or composition can lead to dramatic changes in activity. The possibility that 3I Atlas might have a heterogeneous structure with different materials mixed together in complex ways adds richness to its unfolding story. Perhaps it contains pockets of nearly pure ices surrounded by rocky material, or layers of different composition laid down at different times in its history. As warming penetrates deeper into the object, these different materials would respond differently, creating a complex pattern of activity that evolves over time. It's like watching a time-lapse movie of a landscape changing through the seasons, but the seasons here are measured in months or years, and the landscape is an alien world in miniature. The jets that might develop on 3I Atlas as it warms would be particularly spectacular manifestations of its awakening. These jets, narrow streams of gas and dust erupting from specific locations on the surface, are common features on active comets in our solar system. They occur where subsurface volatiles find pathways to escape, perhaps through cracks or areas of particularly volatile rich material. If 3I Atlas develops jets, they would be fountains of material from another star system, geysers of ancient molecules finally freed from their icy prison. The role of solar radiation in processing the surface of 3I Atlas, even as it causes sublimation, adds another layer of complexity. Ultraviolet photons from the sun can break molecular bonds, creating radicals and ions that can recombine in new ways. This photochemistry might be creating new molecules on the surface even as others are being lost to space. The surface might be becoming more complex chemically, even as it's being eroded physically. A balance between creation and destruction playing out on a cosmic stage. The possibility that 3I Atlas might contain clathrates, cage-like structures, where one type of molecule is trapped within a framework of another, usually water ice, is particularly intriguing. These clathrates can be stable at higher temperatures than pure ices of the trapped molecules, releasing their contents only when the cage structure itself breaks down. If 3 Atlas contains clathrates, the release of trapped gases might occur in sudden bursts rather than gradual sublimation, creating episodic activity that could be dramatic to observe. The changing distance between 3I Atlas and the Sun as it follows its hyperbolic trajectory means that the warming is not constant but varies with time. As it approaches perihelion, its closest point to the Sun, the warming intensifies, potentially triggering new processes or accelerating existing ones. After perihelion, as it recedes from the Sun, the cooling begins and some processes might reverse. Gases that were sublimating might start to recondense, active regions might become dormant, and the object might begin to return to a state more similar to its interstellar configuration. This cycle of warming and cooling is like a cosmic breathing, an inhalation as the object approaches the Sun, and an exhalation as it recedes. But unlike breathing, this is likely a one-time event for 3I Atlas in our solar system. It will never return to experience another warming cycle with our Sun. This makes every observation precious, every moment of activity unique and irreplaceable. We're witnessing a transformation that happens once in millions of years, a brief awakening between long periods of cosmic sleep. The material being lost from 3I Atlas as it warms represents a transfer of matter from another star system to ours. While the amount is tiny on cosmic scales, perhaps tons or at most thousands of tons, it's nonetheless a real, physical transfer of materials across interstellar space. Some of this material will be swept out of the solar system by the solar wind, continuing its interstellar journey. But some might be captured by the gravity of planets or the Sun, becoming a permanent part of our solar system. In this way, 3I Atlas is not just visiting, but leaving a small part of itself behind. The presence of this interstellar guest invites us to look inward, at our own home, and see it with fresh eyes. As we observe 3I Atlas warming in the Sun's rays, releasing gases that have been frozen for eons, developing possibly a coma or even jets, we're reminded that similar processes shaped our own solar system. The comets that we see, the asteroids we study, the meteorites that fall to Earth, all are part of the same cosmic story, just written in a different chapter. 3I Atlas is like a mirror held up to our solar system, reflecting not our present but our past, showing us what we might have looked like billions of years ago when our own materials were still coming together. The comparison between 3I Atlas and objects in our solar system is inevitable and illuminating. How does its composition compare to our comets? Are the organic molecules similar or different? Is the ratio of rock to ice comparable to what we see in our own small bodies? Each similarity tells us about universal processes that operate throughout the galaxy. Each difference tells us about the diversity of conditions under which planetary systems form. It's like comparing notes with someone from a different culture. We learn both what we have in common and what makes us unique. Our solar system contains its own population of comets and asteroids, objects that have been orbiting our Sun for billions of years. These objects, particularly those in the outer solar system that have been least altered by solar heating, preserve materials from the early solar system. They're our own time capsules, our own records of ancient history. By comparing them to 3I Atlas, we can begin to understand whether the processes that formed our solar system were typical or unusual, whether we're a standard model or a cosmic oddity. The Oort cloud, that vast spherical shell of icy bodies that surrounds our solar system at enormous distances, might be our closest analogue to wherever 3I Atlas originated. Objects in the Oort cloud have been in deep freeze since the solar system formed, experiencing conditions not too different from interstellar space. Some of them are occasionally perturbed into the inner solar system, becoming the long-period comets that grace our skies. If 3I Atlas originated in another star's Oort cloud equivalent, comparing it to our Oort cloud comets could tell us about the universality of such structures around stars. The Kuiper belt, that ring of icy bodies beyond Neptune's orbit, provides another comparison point. These objects formed in the cold outer reaches of our solar system and have remained there ever since, relatively unaltered by solar heating. Their compositions, structures, and dynamics tell us about conditions in the outer protoplanetary disk. If 3I Atlas shows similarities to Kuiper belt objects, it might have formed in an analogous region of its parent system. If it shows differences, those differences could tell us about variations in how planetary systems organize themselves. The asteroid belt between Mars and Jupiter offers yet another comparison. These rocky bodies are remnants from the inner solar system's formation, materials that never coalesced into a planet due to Jupiter's gravitational influence. They're generally depleted in volatile compounds, having formed inside the frost line where temperatures were too high for ices to condense. If 3I Atlas shows similarities to asteroids, it might have originated from the inner regions of its parent system, perhaps ejected by gravitational interactions with forming planets. The process of planetary migration, which we now know occurred in our own solar system, provides a framework for understanding how objects like 3I Atlas might be ejected from their parent systems. In our solar system, the giant planets didn't form where we see them today, but migrated to their current positions through gravitational interactions with the disk of planetesimals. This migration scattered countless small bodies, sending some into the Sun, others into the outer solar system, and presumably some into interstellar space. Our solar system must have created its own interstellar objects, cosmic messages in bottles that are now drifting between the stars. The Late Heavy Bombardment, a period about 3.9 billion years ago when the inner solar system was pelted with asteroids and comets, might have been caused by a reorganization of the giant planet's orbits. This event, if it occurred as theorized, would have ejected many objects from our solar system. Some of these objects are now interstellar travelers like 3I Atlas, carrying information about our solar system to distant stars. There's a beautiful symmetry in this. As we receive and study interstellar visitors, other star systems might be receiving and studying visitors from our solar system. The comparison extends to the chemical level. The isotopic ratios we measure in solar system materials tell us about conditions in the solar nebula from which our sun and planets formed. Different isotopes of the same element can have slightly different behaviors in chemical reactions, leading to fractionation that depends on temperature, pressure, and other conditions. If we could measure the isotopic ratios in 3I Atlas precisely, comparing them to solar system values would tell us about similarities and differences in the formation environments. The organic molecules found in our solar system, particularly in carbonaceous meteorites, provide a baseline for comparison with any organics that might be detected in 3I Atlas. These molecules, including amino acids, sugars, and nucleobases, are formed through non-biological processes in space or in the early solar system. If 3I Atlas contains similar molecules, it would suggest that organic chemistry follows similar pathways throughout the galaxy. If it contains different molecules or the same molecules in different proportions, it would tell us about variations in cosmic organic chemistry. The noble gas patterns in solar system materials have been extensively studied and provide unique insights into various processes. Solar noble gases implanted by the solar wind have one pattern. Planetary noble gases trapped during formation have another. Cosmogenic noble gases produced by cosmic ray interactions have yet another. If we could measure noble gases from 3I Atlas, perhaps in gases released during its warming, comparing them to solar system patterns would reveal similarities and differences in stellar and planetary processes. The mineralogy of solar system materials reflects the conditions under which they formed and evolved. Certain minerals only form under specific conditions of temperature, pressure, and chemical environment. The presence or absence of specific minerals in 3I Atlas would tell us about its formation and processing history. For instance, the presence of hydrated minerals would indicate processing in the presence of liquid water, while anhydrous minerals would suggest dry conditions. Each mineral is like a word in the geological language, and reading them together tells the story of the object. The size distribution of particles that might be released from 3I Atlas can be compared to what we observe in cometary dust from our own solar system. This size distribution is influenced by how the particles formed, how they were processed, and how they're being released. If 3I Atlas releases dust with a similar size distribution to our comets, it might indicate similar formation and processing mechanisms. Differences would point to variations in these processes between stellar systems. The magnetic properties of materials from 3I Atlas, if we could measure them, would provide another point of comparison. Some solar system materials preserve magnetic records from the early solar system, when the solar nebula was threaded with magnetic fields. These paleomagnetic records tell us about the magnetic environment during planet formation. Similar measurements from 3I Atlas would reveal whether magnetic fields played a similar role in its parent system. The comparison between 3I Atlas and solar system objects also extends to their dynamics. The way objects move, rotate, and tumble tells us about their internal structure and history. If 3I Atlas rotates in a manner similar to solar system comets or asteroids, it might indicate similar formation processes or collisional histories. Unusual rotation, such as tumbling or very fast or slow spinning, might point to a unique history or structure. By serving as a cosmic mirror, 3I Atlas helps us understand what makes our solar system special and what makes it typical. Every measurement we make, every comparison we draw, adds to our understanding of planetary systems throughout the galaxy. We're not just studying one interstellar object. We're beginning to build a comparative planetology that spans different star systems. It's the beginning of a new field of science, one that will grow as we detect and study more interstellar visitors. The comparison between 3I Atlas and solar system objects extends even deeper when we consider the radiation environment that shaped both. Our solar system objects have been exposed to our sun's particular spectrum of radiation, its solar wind with its specific composition and intensity, its magnetic field with its unique properties. Objects in our solar system bear the signature of these influences written in their surface chemistry, their isotopic ratios, their crystal structures. 3I Atlas bears similar signatures, but from a different star, possibly with a different spectrum, different solar wind, different magnetic field. These differences, subtle as they might be, are like different dialects of the same cosmic language, variations on the universal theme of how stars influence the objects that form around them. As 3I Atlas begins its long, slow departure from our solar system, we are left not with definitive answers, but with more beautiful and profound questions that will resonate through the halls of science for generations to come. Its passage through our lives is fleeting on cosmic scales, measured in just a few years out of the billions of years of our solar system's existence. Yet the wonder it inspires, the questions it raises, and the perspectives it provides will remain long after its faint light has faded beyond our ability to detect it. These new questions are like seeds planted in the fertile ground of human curiosity, seeds that will grow into new research programs, new missions, new ways of understanding our place in the cosmos. The legacy of 3I Atlas begins with the fundamental question of how common such objects really are. If interstellar objects pass through our solar system regularly, which the detection of multiple such objects in recent years suggests, then the space between stars is not the empty void we once imagined, but a highway travelled by countless cosmic wanderers. Each of these objects carries information about its parent system, meaning that star systems throughout the galaxy are constantly, if slowly, exchanging materials and information. This transforms our view of the galaxy from a collection of isolated stellar islands to an interconnected network where materials and perhaps even the building blocks of life flow between stars over cosmic timescales. The question of composition remains tantalizingly open. We've made observations, collected spectra, analyzed light curves, but the exact makeup of 3I Atlas remains uncertain. Is it primarily rocky or icy? Does it contain significant amounts of organic molecules? Are there exotic materials formed under conditions we've never encountered in our solar system? Each possibility opens different avenues of investigation, different implications for planetary formation, different insights into the diversity of materials that exist in planetary systems. The uncertainty itself is valuable, reminding us of how much we still have to learn, how many surprises the universe still holds. The mechanism of ejection that sent 3I Atlas on its interstellar journey raises profound questions about the dynamics of planetary systems. Was it ejected by a close encounter with a giant planet, suggesting that its parent system underwent a period of dynamical instability similar to what we think happened in our own solar system? Was it stripped away by a passing star, indicating that its parent system experienced close stellar encounters that we've been lucky to avoid? Or was it ejected by some process we haven't even considered, some mechanism that doesn't operate in our solar system? Each scenario tells us something different about the variety of evolutionary paths that planetary systems can follow. The age of 3I Atlas remains one of the most intriguing unknowns. Has it been travelling for millions of years, or billions? Did it leave its parent system recently in cosmic terms, or has it been wandering since before our solar system formed? The answer to this question would tell us about the rate at which objects are ejected from star systems, the typical lifetimes of interstellar objects, and the likelihood of exchanges between different stellar generations. If 3I Atlas is very old, it might preserve information about the galaxy's past that's been erased everywhere else by stellar evolution and recycling. The question of whether 3I Atlas is typical or unusual among interstellar objects will only be answered as we detect and study more such visitors. Is its size typical? Its composition? Its velocity? Its trajectory? Each new interstellar object we discover will add a data point, gradually building up a statistical picture of the population. We might find that 3I Atlas is perfectly ordinary, one of countless similar objects, or we might discover that it's highly unusual, a cosmic oddity that challenges our understanding. Either result would be valuable, either confirming our theories or forcing us to revise them. The possibility that 3I Atlas might have passed through other star systems before reaching ours opens fascinating avenues of speculation. Over millions of years of travel, it might have had multiple stellar encounters, each one potentially altering its trajectory, its rotation, its surface properties. It might have been warmed by other stars, accumulating layers of processing like a cosmic palimpsest. If this is the case, then 3I Atlas doesn't just carry information about its parent system, but about its entire journey, a travelogue written in chemistry and physics across millions of years and thousands of light years. The role of 3I Atlas in calibrating our detection capabilities raises practical questions that will shape future observations. How faint can an interstellar object be and still be detected with current technology? How fast can it be moving? How close does it need to pass to Earth? The answers to these questions tell us what fraction of interstellar objects we're currently able to detect, which in turn tells us how many might be passing by unnoticed. This knowledge will drive the development of new survey telescopes, new detection algorithms, new observational strategies designed to catch more of these cosmic visitors. The question of whether we could send a spacecraft to intercept and study an object like 3I Atlas pushes the boundaries of our technological capabilities. The high velocity of interstellar objects means that catching up to one would require enormous amounts of energy, far more than current propulsion systems can provide. But the scientific value of directly sampling materials from another star system is so high that it's driving research into new propulsion technologies, from solar sails to nuclear rockets to concepts we're only beginning to imagine. 3 Atlas might be gone before we could reach it, but future interstellar visitors might not be so lucky, or rather, we might be luckier in our ability to study them. The implications for astrobiology, the study of life in the universe, are particularly profound. If objects like 3I Atlas can carry organic molecules between star systems, then the chemical precursors to life might be distributed throughout the galaxy. This doesn't mean that life itself is transferred, but that the building blocks, the raw materials from which life might arise, could be more widely distributed than we thought. This would increase the chances that life could emerge wherever conditions are suitable, making the universe potentially more biologically rich than we've dared to imagine. The question of whether 3I Atlas could contaminate our solar system with foreign materials raises interesting planetary protection issues. While the chance of biological contamination is essentially zero, given the harsh conditions of interstellar space and the millions of years of travel, the introduction of exotic organic molecules or unusual minerals could theoretically influence chemical processes on any body that 3I Atlas might impact. This is likely not a concern for 3I Atlas specifically, which will leave our solar system without impacting anything. But future interstellar objects might have different trajectories, and we need to consider the implications. The cultural and philosophical questions raised by 3I Atlas are as important as the scientific ones. The confirmation that objects can travel between star systems makes the universe feel more connected, less lonely. We're not isolated on our cosmic island, but part of a vast network where materials and information flow, albeit slowly, between stellar systems. This changes our perspective on our place in the universe, making us feel more integrated into the cosmic community, even if that community communicates only through the exchange of rocks and ice over millions of years. The question of whether interstellar objects like 3I Atlas played a role in the origin of life on Earth adds a new dimension to one of science's most profound mysteries. If the early Earth was seeded with organic molecules from interstellar objects, then life on our planet might have gotten a head start, beginning with complex molecules that would have taken much longer to form locally. This wouldn't diminish the wonder of life's emergence, but would add another chapter to the story, connecting us even more intimately to the cosmos. We wouldn't just be made of star stuff, as Carl Sagan famously said, but potentially of interstellar stuff, materials that have traveled between stars before finding their way into our bodies. The technological questions raised by studying 3I Atlas will drive innovation for years to come. How can we better detect faint, fast-moving objects? How can we quickly determine their orbits and compositions? How can we mobilize observational resources rapidly when a new interstellar object is discovered? These challenges are pushing us to develop new technologies, from artificial intelligence systems that can automatically detect unusual objects in survey data to rapid response telescope networks that can begin observations within hours of a discovery. The legacy of 3I Atlas will include not just scientific knowledge, but technological capabilities that will benefit many areas of astronomy. The question of what 3I Atlas tells us about the future of our own solar system is sobering and inspiring in equal measure. Our sun will not burn forever, and as it ages it will change, eventually expanding into a red giant and then contracting into a white dwarf. During these transitions, many objects in our solar system will be ejected, becoming interstellar travelers themselves. Perhaps billions of years from now, one of our asteroids or comets will pass through another star system, where alien astronomers might observe it and wonder about its origins, just as we wonder about 3I Atlas. We're not just observers of this cosmic process, but participants in it. The statistical questions raised by 3I Atlas require us to think probabilistically about rare events. If we've detected a few interstellar objects in just a few years of looking with modern surveys, what does this tell us about the total population? How many such objects are there per cubic light-year of space? How often does one pass within a certain distance of Earth? These calculations require careful statistical analysis, accounting for observational biases, detection efficiencies, and the vast scales of space and time involved, the answers will tell us whether interstellar objects are rare curiosities or common features of the galactic environment. The question of whether 3I Atlas represents a new class of objects or is part of a continuum with solar system objects challenges our classification schemes. We like to put things in neat categories: asteroids, comets, planets, moons. But nature doesn't always respect our categories, and 3I Atlas might be showing us that the boundaries between different types of objects are fuzzier than we thought. Perhaps there's a continuous distribution of objects from purely rocky to purely icy, from solar system natives to interstellar visitors, with no clear dividing lines. This would require us to think more flexibly about cosmic taxonomy, to embrace gradients and continuities rather than rigid categories. The preservation questions raised by 3I Atlas extend to how we archive and share the data collected during its passage. The observations made of this object need to be preserved for future scientists, who might have new techniques for analysis, new theories to test, new questions to ask. This requires robust data archives, standardized formats, and international cooperation to ensure that the information remains accessible for decades or centuries to come. The data from 3I Atlas will outlive the astronomers who collected it, becoming part of humanity's permanent record of cosmic exploration. The question of what we might have missed in our observations of 3I Atlas will haunt astronomers for years. Were there subtle features in its spectrum that we didn't have the sensitivity to detect? Were there variations in its brightness that we didn't observe because we weren't looking at the right times? Did it experience outbursts or fragmentations when no telescopes were pointed at it? These unknowns remind us that even our best observations are incomplete, that there's always more to learn if only we had better instruments, more observing time, or simply better luck in what we happen to observe. The educational questions raised by 3I Atlas involve how we teach the next generation about the universe. The existence of interstellar objects adds a new chapter to astronomy textbooks, a new concept for students to grapple with. It makes the universe feel more dynamic, more interconnected, more surprising than the static picture often presented in introductory courses. Teachers will use 3I Atlas as an example of how science progresses, how new discoveries challenge old assumptions, how the universe continues to surprise us even after centuries of observation. The question of whether 3I Atlas could inspire new space missions is already being answered in the affirmative. Scientists and engineers are designing missions that could intercept future interstellar objects, using technologies like solar sails or ion drives to achieve the high velocities needed to catch these cosmic speedsters. These missions would require international cooperation, long-term planning, and technological innovations that push the boundaries of what's possible. The dream of directly sampling materials from another star system, inspired by objects like 3I Atlas, might drive space exploration for decades to come. The philosophical questions about identity and persistence raised by 3I Atlas touch on deep issues in metaphysics. Is 3I Atlas the same object that left its parent system millions of years ago, or has it been so transformed by its journey that it's essentially a different entity? If it fragments, are the pieces still 3I Atlas, or do they become new objects? These might seem like abstract philosophical concerns, but they have practical implications for how we track and study objects over time, how we maintain continuity of observation, how we connect current observations to future ones. The question of what 3I Atlas means for the search for extraterrestrial intelligence adds an intriguing dimension to SETI research. While 3I Atlas itself is almost certainly a natural object, its existence proves that materials can travel between star systems. This raises the possibility, however remote, that an advanced civilization could use such objects as a means of communication or exploration, sending probes disguised as natural asteroids or comets. This doesn't mean we should assume 3I Atlas is artificial, but it does mean we should carefully examine interstellar objects for any signs of artificial modification or embedded technology, just to be thorough. The climatic questions raised by 3i Atlas involve what would happen if such an object impacted Earth or another planet. While 3i Atlas itself poses no threat, passing harmlessly through our solar system, future interstellar objects might have Earth-crossing orbits. The high velocity of interstellar objects means they would carry enormous kinetic energy, potentially causing more damage than a similar-sized object from our own solar system. This adds a new dimension to planetary defense considerations, requiring us to monitor not just solar system asteroids and comets, but also interstellar visitors. The question of how common systems like ours are in the galaxy is illuminated by 3i Atlas in unexpected ways. If most planetary systems regularly eject objects like 3i Atlas, then dynamical instability might be common during planetary system evolution. This would mean that many systems go through periods of chaos and reorganization, with planets migrating, colliding, or being ejected entirely. Our solar system's current stability might be the exception rather than the rule, or it might be a phase that many systems eventually reach after early periods of instability. The chemical questions raised by 3i Atlas extend to the formation of specific molecules under conditions we can't replicate on Earth. The combination of extreme cold, high radiation, and million-year timescales in interstellar space might produce exotic molecules that don't exist anywhere else. These molecules might have unusual properties, perhaps serving as catalysts for reactions we haven't imagined, or storing information in ways we haven't considered. The chemistry of interstellar space, as exemplified by objects like 3i Atlas, might be far richer and more complex than we've assumed. Finally, we bring our journey to a peaceful close, zooming out from the fading light of 3i Atlas to encompass the quiet, sprawling galaxy in which this cosmic drama has played out. As we pull back our perspective, 3i Atlas shrinks from a distinct object to a point of light, then disappears entirely into the vast darkness between the stars. Yet its invisibility doesn't mean it ceases to exist or ceases to matter. It continues on its eternal journey, carrying its cargo of ancient materials and cosmic secrets toward distant stars we can barely see, toward encounters that won't occur for millions of years, toward a future as vast and uncertain as its past. The mystery of our visitor dissolves into the greater mystery of the cosmos itself, a universe filled with countless other secrets drifting in the silent darkness. How many other objects like 3i Atlas are out there, sailing between the stars, each one a message in a bottle from a distant stellar shore? Thousands, millions, billions. The number is almost certainly larger than we can properly comprehend. A vast flotilla of cosmic wanderers, each following its own trajectory through space and time, most never coming close enough to any star for anyone to notice their passage. They are the universe's quiet messengers, carrying information between stellar systems with infinite patience, connecting the galaxy in a slow network of material exchange. As you settle into rest tonight, feel your connection to this vast and wonderful emptiness, knowing that you are a small but meaningful part of an endless unfolding story. The atoms in your body, forged in the hearts of dying stars and scattered through space in supernova explosions, have their own cosmic history. They've been part of interstellar clouds, perhaps incorporated into other planets around other stars, maybe even carried between stellar systems by objects like 3i Atlas. You're not separate from the cosmos, but woven into its very fabric, a temporary arrangement of ancient materials that will eventually return to the cosmic cycle, perhaps to travel between stars yourself, atom by atom, over the eons to come. The questions can wait, for they are patient questions, cosmic questions that have existed since before Earth formed and will persist long after our sun has died. Questions about how planetary systems form and evolve, about whether life exists elsewhere, about the ultimate fate of the universe itself. These questions don't demand immediate answers but invite contemplation, wonder, and gradual understanding. Each generation of humans adds a little more to our knowledge, passes the torch of curiosity to the next. and the great conversation between humanity and the cosmos continues. 3 Atlas has contributed its verse to this conversation, and now it's up to us to listen, to interpret, to respond with our own questions and discoveries. For now, there is only the quiet, and the stars, and the knowledge that somewhere out there, 3 Atlas continues its journey through the darkness. In a few years, it will be too faint for even our most powerful telescopes to detect, lost again in the vast ocean of interstellar space. But it won't be gone, merely invisible, continuing its patient traverse of the galaxy. Perhaps millions of years from now, it will warm again in the light of another star, maybe one that doesn't even exist yet. A star that will be born from the collapse of a molecular cloud that's currently drifting peacefully through space, and perhaps around that future star, on a planet that hasn't yet formed. Beings we can't imagine will detect this ancient visitor and wonder about its origins, just as we've wondered during its brief passage through our lives. The silence of space is not empty, but full of potential, pregnant with possibilities we're only beginning to glimpse. Every point of darkness might hide an interstellar traveller. Every faint smudge of light might be a visitor from another star system. Every observation might reveal something that challenges our understanding and expands our horizons. The universe is not a static painting, but a dynamic, evolving system where matter and energy, information, and perhaps even life flow in patterns we're only beginning to discern. 3 Atlas has shown us one thread in this vast tapestry, and following that thread has led us to contemplate the entire weaving. Consider how your perspective has shifted during our journey together tonight. We began with a simple question about a faint object detected by our telescopes, and we've travelled through considerations of cosmic chemistry, stellar evolution, planetary formation, and the interconnectedness of all things in the universe. We've thought about timescales that dwarf human experience and distances that challenge human comprehension. We've considered possibilities that would have seemed like fantasy just a generation ago, but are now the subject of serious scientific investigation. This expansion of perspective, this growth of wonder, is perhaps the greatest gift that objects like 3 Atlas offer us. The cosmic perspective that 3 Atlas provides is both humbling and elevating. Humbling because it reminds us how small we are, how brief our existence, how limited our current understanding. But elevating because it shows us that we're part of something magnificent, a cosmic story billions of years in the making and billions of years yet to unfold. We're not merely observers of this story, but active participants, capable of detecting and studying objects from other star systems, of understanding processes that occur on scales vast beyond imagination, of asking questions that probe the deepest mysteries of existence. As the night deepens around you, let your mind drift with 3 Atlas through the cosmic darkness. Imagine the profound cold of interstellar space, where molecules barely move and time seems to slow to a crawl. Imagine the sudden warmth of approaching a star, the gradual awakening of frozen materials, the brief flourishing of activity before returning to the cold and dark. Imagine the countless stars 3 Atlas has passed in its journey, each one a sun, perhaps warming its own family of planets, perhaps harbouring its own forms of life, perhaps sending out its own interstellar messengers to drift through the galaxy. The rhythm of the cosmos is slow and patient, measured not in heartbeats or years, but in the orbits of stars around the galactic centre, the lives and deaths of stellar generations, the gradual evolution of the universe itself. 3 Atlas moves to this cosmic rhythm, its journey a single note in a symphony that's been playing since the Big Bang, and will continue until the universe reaches whatever end awaits it. We've been privileged to hear this note during its brief crescendo as it passed through our solar system. But the music continues whether we're listening or not, an eternal composition written in the movements of matter and energy through space and time. The darkness between the stars, which might once have seemed empty and frightening, now reveals itself as full of travellers, each one carrying stories we're only beginning to learn how to read. The void is not void, but rich with possibility. crossed by invisible highways of gravitational influence, peppered with wandering fragments of distant worlds, threaded with magnetic fields and stellar winds that shape the journey of every traveller. 3 Atlas has shown us that interstellar space is not a barrier, but a medium through which the galaxy's star systems communicate, however slowly, however indirectly. As your consciousness begins to drift towards sleep, let the vastness of space cradle your thoughts. The same physical laws that govern 3 Atlas's journey through the cosmos govern the atoms in your body, the neurons in your brain, the very thoughts you're thinking. You're not separate from the universe, but an expression of it, a way for the cosmos to observe and understand itself. Through your eyes, the universe has watched 3 Atlas pass by. Through your mind, it has contemplated the meaning of this passage. Through your wonder, it has experienced awe at its own majesty. The questions that 3 Atlas leaves behind are not burdens but gifts, invitations to continue exploring, to keep wondering, to maintain the curiosity that makes us human. Each question leads to new observations, new theories, new understanding, and inevitably new questions. This is the nature of science, the nature of human inquiry, the nature of our relationship with the cosmos. We'll never have all the answers, and that's not a failure but a blessing. It means the universe will never cease to surprise us, never run out of mysteries to explore, never stop inspiring wonder in those who take the time to look up at the stars and ask, what if? The story of 3 Atlas is far from over. As it continues its journey through interstellar space, it carries with it not just its ancient materials, but now also the tiny gravitational influence of its encounter with our Sun, a minute change in its trajectory that will affect where it goes next. In this small way, our solar system has left its mark on this interstellar visitor, just as the visitor has left its mark on us. We've exchanged influences across the vast gulf between star systems, a cosmic handshake that connects us to the wider galaxy. Somewhere in the galaxy, perhaps right now, another interstellar object is being ejected from its parent system, beginning a journey that might bring it to our neighborhood millions of years from now. Somewhere else, an object that left its system billions of years ago is approaching another star, about to be discovered by observers we'll never meet. These cosmic wanderers form a vast, slow circulation system that connects all the star systems in the galaxy, mixing materials, distributing chemical elements, perhaps even spreading the seeds of life. 3 Atlas has shown us that we're part of this system, not isolated but connected to every other star and planet in ways we're only beginning to understand. The peace that comes from contemplating these vast scales and slow processes is profound. The urgent concerns of daily life fade into perspective when considered against the patient journey of 3 Atlas. The conflicts and competitions that consume so much human energy seem less important when we realize we're all made of the same cosmic materials, all passengers on the same small planet, all participants in the same cosmic story. This perspective doesn't diminish the importance of human concerns, but places them in a context that can bring clarity and calm. As sleep approaches, let your last thoughts be of gratitude. Gratitude that we live in a time when we can detect and study objects like 3 Atlas. Gratitude for the scientists and engineers who built the telescopes and developed the techniques that make such observations possible. Gratitude for the cosmic processes that created and delivered this interstellar visitor to our doorstep. And gratitude for the capacity to wonder, to question, to seek understanding of our place in the vast cosmos. The universe continues its patient unfolding whether we're awake or asleep, whether we're watching or not. Stars are being born and dying, planets are forming and evolving, and countless objects like 3 Atlas are drifting through the darkness, each one a story waiting to be told. Some of these stories we'll discover and read, others will pass by unnoticed, their secrets preserved for future observers, or perhaps never revealed at all. But knowing that these stories exist, that the universe is rich with mysteries and wonders we've yet to discover, makes our existence more meaningful, our curiosity more justified, our wonder more appropriate. Rest now, knowing that you're part of this grand cosmic narrative. Your atoms have travelled across the galaxy, your molecules have been assembled from cosmic ingredients, your consciousness has emerged from the same physical laws that govern 3i Atlas and every other object in the universe. You're not a separate observer, but an integral part of the cosmos, a way for the universe to know itself, to appreciate its own beauty, to wonder at its own mysteries. In contemplating 3i Atlas, you've participated in the universe's self-contemplation, adding your voice to the eternal conversation between mind and cosmos. The stars continue their ancient dance, the planets pursue their ordained orbits, and somewhere in the darkness, 3i Atlas continues its eternal journey, carrying its secrets toward distant suns and future revelations. The cosmos is vast and patient, mysterious and beautiful, foreign and familiar all at once. We're blessed to be conscious at this moment, able to perceive and ponder these cosmic truths, able to feel both the vastness of space and the intimacy of understanding. The universe has given us a gift in 3i Atlas, a glimpse of the infinite stories drifting through the darkness, waiting to be discovered, waiting to expand our horizons, waiting to remind us that we're part of something far grander than we often remember. Sleep peacefully, cradled by gravity, warmed by our local star, protected by our planet's atmosphere and magnetic field, surrounded by the vast cosmos that created you and to which you'll eventually return. The questions will still be there tomorrow, the mysteries will continue to unfold, the universe will keep its secrets and slowly reveal them to those patient enough to look and listen. For now, let the cosmic perspective bring peace. Let the vast scales bring calm. Let the eternal journey of 3 Atlas remind you that some things transcend the momentary concerns of daily life. The universe is vast and wonderful, full of mysteries we've yet to discover, stories we've yet to hear, connections we've yet to make. 3i Atlas has shown us one small part of this cosmic tapestry, but there's so much more to explore, so much more to understand, so much more to wonder about. This is not an ending but a beginning, not a conclusion but an invitation to continue the journey of discovery that makes us human. The cosmos awaits, patient and eternal, ready to reveal its secrets to those who dare to look up and wonder. In the silence and the darkness, in the space between breaths and the pause between heartbeats, feel your connection to the cosmos. You're made of star stuff, as are we all, temporary arrangements of eternal atoms, brief flames of consciousness in an universe that may be far more aware than we yet understand. 3 Atlas is our cousin in this cosmic family, made of the same fundamental particles, governed by the same physical laws, participating in the same grand story of cosmic evolution. Its journey and ours are different chapters in the same book, different verses in the same infinite poem. The night is deep now, and sleep calls with its promise of rest and dreams. Perhaps tonight you'll dream of drifting through interstellar space, feeling the profound cold and silence, the patience of cosmic time, the slow dance of gravity and momentum. Perhaps you'll dream of other worlds orbiting other stars, of the formation of planets from swirling disks of dust and gas, of the emergence of complexity from simplicity over billions of years. Or perhaps you'll simply rest, your mind quiet, your body still, participating in the same cosmic peace that embraces 3i Atlas in its eternal journey. The universe continues its patient unfolding, indifferent to our observation but enriched by our understanding. Each discovery, each question, each moment of wonder adds to the sum of cosmic self-awareness. We are the universe's way of knowing itself, and through us, it experiences awe at its own majesty. 3i Atlas has been our teacher tonight, showing us the connections between star systems, the patience of cosmic processes, the richness of mysteries yet to be solved. we've learned not just about an interstellar object, but about our place in the grand scheme of things, our connection to the cosmos, our participation in the eternal dance of matter and energy through space and time. As consciousness fades into sleep, let your last thought be of wonder. Wonder at the vastness of space, the depth of time, the richness of cosmic processes. Wonder at our ability to detect and study objects from other star systems. Wonder at the questions we can ask and sometimes answer. Wonder at the mysteries that remain, inviting future generations to continue the quest for understanding. And wonder at the simple fact that we exist at all, conscious beings capable of contemplating our cosmic context, of feeling awe at the universe that created us. The stars watch over your sleep, as they've watched over the sleep of every human who ever lived, as they watched over the earth before life emerged, as they'll watch long after we're gone. They are distant suns, each perhaps warming its own worlds, each participating in the same cosmic processes that created our solar system and ejected 3 of us Atlas on its interstellar journey. In their light transmitted across vast distances, we see not just points of brightness, but connections to the wider universe, reminders that we're not alone but part of a vast cosmic community. Rest now, peaceful in the knowledge that the universe continues its wonders, whether we're watching or not, that mysteries abound for future discovery, that questions lead to understanding, and understanding leads to new questions in an eternal cycle of learning and wonder. The Atlas continues its journey through the darkness, carrying its ancient secrets toward unknown destinations. And we continue our journey too, orbiting our star, spinning through space, participants in the same cosmic dance, made of the same stellar materials, governed by the same universal laws, united in our shared cosmic heritage. The cosmos is vast and patient, mysterious and beautiful, and we are part of it all. Sleep peacefully, dream deeply, and remember that you are made of stars, connected to every atom in the universe, a conscious expression of cosmic evolution, a way for the universe to know and appreciate itself. The questions can wait until tomorrow. For now, there is only peace, only rest, only the quiet turning of the earth beneath the eternal stars, only the slow breath of sleep as you join the cosmic rhythm of rest and renewal, of ending and beginning, of questions and wonder without end.